Welcome you all to this kickoff meeting of the RISEnergy project. My name is Peter Holtappels. For those who do not know me, I'm from KIT, Karlsruhe Institute of Technology, and I'm coordinating scientifically this project. I'm really happy to see so many of you here, and we also have a lot of people joining online, so I hope this will work. I would like to thank you all for joining, and I would like to thank especially the representation of the state of Baden-Württemberg to host us here for this event. And with this, I would like to hand over to Bodo Lehmann from the representation. So please.
Ja, lieber Herr Holtappels, vielen Dank für die freundliche Begrüßung. Dear ladies and gentlemen, grüß Gott, as we say in southern Germany, and welcome here to the representation of the state of Baden-Württemberg to the European Union. I would like to welcome you all also on behalf of State Secretary for Political Coordination in Europe, Florian Hassler, who sends you all his very best greetings. We are all very pleased that you have decided to host your event and your conference here at our representation to come together at Baden-Württemberg, in Baden-Württemberg, at a spot where Baden-Württemberg meets Brussels. It is very nice to having you all here. And perhaps it doesn't come as a surprise that you meet here in Baden-Württemberg. We have the KIT, Mr. Holtappels, leading this project, but we also do have in Baden-Württemberg a government who has the ambition, and I think we can also say the ambitious ambition, to have climate neutrality not only by 2050, but already by 2040. As you all know, the European Union has set itself the ambitious and important goal to achieve climate neutrality by 2050. Achieving this goal will not be an easy task, but funding and supporting projects such as RISEnergy put us on the right track and on the right path. RISEnergy is a truly European project which brings together organizations across 22 countries, and most of the countries or representatives from those countries are here today or are connected online. I'm particularly happy, and I said that before, to welcoming you all here in our representation. And I'm also very happy that your kickoff meeting takes place here. But then again, Mr. Holtappels, how could it be different with a project led by the KIT? I most likely do not need to tell all of you here about how the Karlsruhe Institute of Technology is unique in Germany and thus such a scientific highlight for the state of Baden-Württemberg. Yet the KIT is not only important at the state and federal level in Germany, but it also is, at least in my opinion, an example for the European Union as a whole, as its lead for the RISEnergy underlines impressively. Ladies and gentlemen, projects such as RISEnergy show just how key research and innovation are for the future of Europe, how key research and innovation are to attaining the goals that the political level of the European Union and its member states have set. Dear guests, I wish you many useful discussions, a productive conference, as well as a great stay here with us at Baden-Württemberg in Brussels. Welcome again, and Mr. Holtappels, I think you take over the floor again, so the floor is yours again. Welcome.
Okay. Good. Thank you, Mr. Lehmann. And I hope actually also that we have a very fruitful event the next 2 half days, basically. RISEnergy is a large project, and also we have a large scope. And this kickoff meeting has a special philosophy, a little bit different from other European kickoff projects, because today we would focus actually on the core of our project, the research infrastructure, which are available for transnational access. And I will also explain a little bit how this event supports the overall objective of the projects. Whereas then tomorrow we will have what I would call the normal kickoff meeting, where we actually go through the administrative issues, the practicalities of the project. So let me briefly introduce you the project in a glance. First of all, at KIT, such a big project is not managed by one person, and I'm very happy that I have a coordination team behind me. And here you see the people, Olga Sominska-Ebersold, Miriam Jill Badaji, Sabine Müller, and Holger Isen. You may have noticed that from all of these people, you have received probably some mails. Again, so this is how we are set up. And especially Miriam and Olga will be involved in the work package management, work package 2 and 5. Sabine is looking on the administrative issues, and Holger is on the strategic level, consulting us. When we set up this project, it was a response to the infrastructure call in 2023. And the ambition from the European Commission was actually that research infrastructures should be grouped across the sectors. And especially here, it was focused on bringing the different fields together in renewable energy technology. And you see the fields which are mentioned in the call, actually 10 areas, which should actually be covered by the project. And to that request, we responded by looking up what kind of research infrastructure projects are available in individual areas, and also addressing them relevant for us. So here you see stories and ERIGRID and enables, which are actively involved. And it took almost a year from submitting the proposal to this date here to finally kick off the project. And if you are interested in the different stages, you can look at the slides later on. The 10 target areas here are listed. We have given them some symbols. Some symbols are coming from ERA. Some others we added. And the challenge is actually how can we bring these different areas together? We have realized in the preparation meetings for the proposal already that there's some different thinking in the different communities, different terminology. So how can we actually bring these fields together? This is in addition to provide access to the excellent infrastructures in this area, a challenge we would like to address in this in order to build a renewable energy technology ecosystem. So the consortium at a glance is stated here. You see on the map, we are spreading across Europe with partners and also infrastructure providers. The budget is 14.5 million euros, and the large portion of this is actually going into the transnational access. There's not that much resources and budget foreseen for road mapping activities, as for example in other projects. So here we are challenged actually to spend this money and to make efficient use of our installations. You also see we have 68 organizations receiving funding directly from the project. We have 84 infrastructures in the project, 81 physically and 3 virtual infrastructures, and 22 countries are involved. So with this project, we would like to initiate a more long-term coordinated effort, actually, with the aim to really scale up renewable energy technologies here in Europe. Okay. As always, we have different objectives proposed, and I will briefly go through them. The first objective is to enable research and innovation to increase the energy efficiency and reduce the cost of energy technology. This is basically also through the transnational accesses, which is then the second objective, provide a transnational access and virtual access. Also, by that, training people actually in using these special infrastructures. But we would like to, as I said, put this on a higher level and in a different context to really lay the foundation for a research infrastructure ecosystem, which then reaches out to all relevant stakeholders. And relevant stakeholders is on the technology side, in the different areas, the researchers, the active persons and people, but also on the different level, the researchers, the political level, the stakeholders, the decision makers. The fourth objective is then supporting objective number 3 is that we have also what we call cross-research infrastructure services. These are actually topics which go beyond the different areas. For example, information and communication technology, but also handling of data, create metadata structures, look at life cycle assessment and materials, and also digitalization in forms of digital services and digital twins. Then also supporting activities are the objectives 5 and 6, devoted to education and training. And finally, that group should become a kind of reference organization to guide the further development in these technology areas and towards the renewable energy system. So how we have structured the project, we actually have the objectives 1 and 2, innovation management and the user access, the transnational accesses, which are strongly linked, also supported by cross-cutting services in terms of ICT, but also in terms of best practices. Here we have a forecasting element, road mapping and perspective, and also it should guide actually the innovation activities where is specific action needed. Then we have this in total should contribute to the objective 3, strengthening the innovation and create the ecosystem. And by this, we have external layers. We have a selection panel from external experts, which help us actually selecting the best use cases and the best proposals for the infrastructure accesses. And we have an external advisory board guiding us then strategically through our journey. A little bit to the organization. We have participants, which are direct contractors to the European Commission. We have affiliated entities and subcontractors, and these are actually the participants receiving money directly. Then we have an extended network advisory board and selection panel as an outer layer. And here you see again the project core with the numbers here, 17 participants and 36 affiliated entities and 15 subcontractors. The participants are listed here, all well-known institutions and also institutions like DERLAB experienced in research infrastructure projects. The affiliated entities are affiliated to 4 different partners, as you see here. ERA is hosting the majority, but also EU Solaris, Network and Excel, and DERLAB have their affiliated entities. The subcontractors you see here to the different partners. With KIT as a coordinator, we take care on a bunch of subcontractors and also AIT in Austria, IMEC and UCC. So the external layer, we have an advisory board, which is actually composed by representative of the different technology areas. We have 10 experts here. The selection panel, so far we have 69 experts also from the various fields, which actually have an active role in ranking the proposals we receive. And the extended network is a group of stakeholders who have actually expressed interest in following the project. The management structure, just very brief. Of course, as each EU project, we have a general assembly of all the beneficiaries, the 17 partners. We have a steering committee, which is composed of the work package managers, but also the representative of the different technology areas, so that we link the operational execution of the project to the content and the technology field. Then the extended networks provides input to the steering committee and also the selection panel and the advisory board to the overall project. This is the RISEnergy project at a glance. And what we would like to do now is we would like to start introducing the research infrastructures from the different fields by actually having presentation from the thematic leaders of the different fields. But before we go to this, are there any questions to the general frame and setup? We will also deal with this tomorrow and more in details how we actually think of running that project. Unless you have comments or questions, then I would start to kick off now what I would call the scientific technical really content, the meat on the bone, I would say, of our project. That we move on to the research infrastructure presentations, the task 3. Okay? Good. So again, a brief recap what I said before. We have the main objective of the project, and what is important now at this stage, I think, are the first 3. This is really supporting the research and innovation, and that we do by providing a unique access point by this project, by the website, by the tools we have, and use actually the outcome of what we do in our transnational accesses, but also in the cross-cutting services to start with a global level advice to the different stakeholders regarding different aspects like life cycle assessment, information communication technology and networking issues. We do this as a core instrument by having these transnational accesses, physical and virtual. And we would like to develop this further to create this ecosystem. And when I heard the term ecosystem the first time, I was actually looking back into my school age when I learned about biology and ecosystems. There, it's very complicated, different kind of tracks, different roads, but all kind of linked together. And looking on our scene, what we have so far is basically we have the different areas which run more or less independently right now. The idea behind this, that if we look into renewable energy technology systems, we will not have one solution fits all. We will have a combination due to resources, due to local availability, due to fluctuations, so several constraints about this. So the first step I hope we achieve with this project, that we identify which technology areas actually could play together and make a game changer by doing this. And this is not a new thing. Actually, before I joined KIT, I was working at DTU, the Technical University of Denmark, and something very interesting happened. It was actually that in classical engineering disciplines, electrical engineering was put together with wind energy. And I think that goes into the direction to look at challenges and to combine the skills and competences needed to address the challenges. So wind energy and system, I think, have something to go together. There may be other areas which are probably not identified, or at least not known to me, but probably to you much better, where that also would make a difference. But at the end, hopefully we come to something that this goes all together, that we see what are the strengths and weaknesses in the different combinations, what fits and what does not. So this is basically my vision for that project, that I don't know if we come to that or here, but that we start the discussion and the thinking for this. So here are the different areas, and the first step of bringing areas and people together is actually learning them to know. And that is the motivation for this afternoon here, that now the thematic leaders of these different areas, here are the 9 technology areas, but also the cross-cutting issues which we have addressed to materials research and development and to international infrastructures, that the experts here present what is in our catalog of infrastructures, not going into each installation or unit, but summarizing them, what is the main challenge in the field, and how could we envisage that these infrastructures contribute to solving them right now. Also as a kind of inspiration for the coffee breaks and also for the networking dinner this afternoon, what we can do. And I hope that yeah, you take this invitation and you actively participate in developing this understanding further. So with this, I hand over to the first topic. It's Ivan Gordon on photovoltaics.
Okay, thanks a lot, Peter. So hello, everybody. So my name is Ivan Gordon. I'm from IMEC in Belgium, and I'm also coordinating the joint program on photovoltaics within ERA. And so I will indeed explain a little bit about the state of the art of photovoltaics and the main issues and how we address them in this project. So here on this curve, this is the so-called learning curve of photovoltaics. You basically see the evolution of the cost. And the main thing to remember from this slide is that at the end of 2023, typically a PV module costed around 20 cents per watt peak. And that is a factor of 1,000 times smaller than 45 years ago when we started measuring this curve. So the PV module cost has increased substantially during the last decades. And that has, of course, led to massive installations worldwide. So here you see, as a function of the year, the total amount of PV modules that were worldwide installed, so the total capacity. And so we see that at the end of 2023, worldwide, there was around 1.5 terawatt, so 1,500 gigawatt on PV capacity active. And you see that especially in the last years, this increased very rapidly with rates of 20 to 30% of extra installations per year. If we look to the technology behind these PV panels, we can say that currently around 95% of the PV panels are based on crystalline silicon. That means we have crystalline silicon wafers as the active absorber material. The other 5% of the PV modules that are there, that can be bought, they are based on so-called thin film alternatives, where instead of crystalline silicon, you use, for instance, cadmium telluride or copper indium gallium diselenide. But so in this project, we focus on crystalline silicon mostly. And so now I will go through quite quickly a few of the main challenges that we are still facing. Because often we hear people saying, okay, photovoltaics, it's very cheap. We already have a very large production, so it seems to be a mature technology. So everything is probably already done. What is there still to do in terms of research? Well, there is actually quite a lot to do. So the first challenge that we are facing is that we have now around 1.5 terawatt of PV worldwide installed and active. But we know that to become climate neutral by 2050 or perhaps earlier, we actually have to go to 50 or 60 terawatt. So we are only at the start. And so we have only, we have less than 30 years actually to go from 1.5 to 50 or 60 terawatt. So that means that the annual production, which is at the moment around 300 gigawatt of PV modules produced per year, has to probably go up in the coming years by a factor of 5 to 10, which poses a lot of problems, especially logistically, but also in terms of where are we going to install all these PV panels. And especially in densely populated areas like Western Europe, it's not always easy to find a lot of space. And that's the second challenge then. You see more and more so-called integrated photovoltaics appearing. So what it means is on the left-hand side, you see the standard PV applications where typically we are used to that somebody puts PV panels on their roof, or you have a big field where you have a lot of PV panels. But we see now, and this is very needed, that there are more and more so-called integrated PV applications appearing where the PV modules are really seamlessly integrated into their environment. So you see some examples here. It can be integrated in a building, so not just placed on the roof, but for instance, part of the facade. It can be integrated in a vehicle. It can be integrated in the road. It can be floating, even on the sea or on a pond. And also something that is attracting a lot of attention is so-called agrivoltaics, where you actually combine agriculture with energy generation by PV. And so the main thing here is always that you use actually a certain area for multiple purposes, including electricity generation. Then a third challenge, and this is really one of the main ones in my view, is the sustainability. So we have to start even more massively than what we are doing today, producing a lot of PV panels. And this poses a lot of problems in terms of sustainability and material usage. On the one hand, of course, we have to think also about recyclability. So we can recycle the current PV modules, but it's still, let's say, a difficult, complicated process that can also be expensive. So we have to think about, can we design in the future our PV panels better so that they are easier recyclable? But also we are consuming a lot of materials. So, and I give here the example of silver. So a PV module, a crystalline silicon PV module, typically contains a few grams of silver. That is because of metal contacts of the solar cells. A few grams doesn't sound like a lot, but since we are producing roughly 1 billion panels per year, this few grams per PV module corresponds to thousands of tons of silver. So at the moment, we are already in the PV sector consuming around 15% of the total silver that is produced per year just for PV alone. If we have to go to a factor of 10 more in production, this is of course going to be problematic. So in this right-hand side curve, you see actually some target numbers of how much silver we can actually allow per gigawatt of produced PV. And all technologies at the moment are still way above that. And then the final challenge is we still have to go to higher efficiencies and higher energy yield. So I showed you this 20 cents per watt peak, which is the cost for a PV module. But in fact, if you're going to install PV modules, you install a whole system. And if you look to this total system cost, the cost of the PV modules at the moment is only 1/3, and it's going to drop further. So the balance of system, as we call it, is actually responsible for 2/3 of the cost. So if you have higher energy yield and higher efficiency of your panels, then you need a lower area to have the same power generation, and this will in the end also reduce the cost a lot. So one of the main things that are being done at the moment is to go to so-called tandem devices. So with crystalline silicon solar cells, the record efficiency, energy conversion efficiency is 27%, and this is very close to the theoretical limit. So what we are going to do as a next step is we are going to put a second solar cell on top of the silicon, which should have a higher band gap. And in this way, we can reach actually efficiencies well above 30%. And of course, we also have to look to the operational lifetime. We have to increase the lifetime of the devices so that they actually, during the lifetime, also generate more electricity. So both are needed, higher efficiencies and higher energy yields to go to even further lower costs. So how do we address that now in the project? So in our project, we have 4 research infrastructures that are fully dedicated to PV. There are also a few others which are cross-cutting, where PV is involved. And with these 4 research infrastructures, we focus on crystalline silicon, and we cover the whole value chain, including also going to the tandems. And in this way, this will help to further speed up the necessary developments. So basically, we can, with our research infrastructure, address these 4 challenges that I have just shown you. So we can quickly go through them. So we have 2 research infrastructures, one in Norway and one in Turkey, where we actually focus on the silicon solar cells. So we have on the one hand in Norway, we look to the material, so the silicon material itself. There is still lots of room for improvements there. And in Turkey, then we have a very nice pilot line actually, where we can make all kinds of crystalline silicon cells and even also modules. Then at Energyville here in Belgium, so this is my own lab, we actually will focus on the silicon perovskite tandems, so the next generation where we put a thin film material, in this case a perovskite material, on top of the silicon to go to efficiencies above 30%. And then we also have the Sol PV lab from CENER in Spain, where actually we have really state-of-the-art indoor and outdoor testing, which is also very important, especially for all these different applications that we see appearing in the market. So yeah, that's basically a short summary for the PV part of RISEnergy.
Thank you. So, oops. Are there any questions for Ivan? Seems not. Then not here online questions. Okay. Then we try to get the online question into the room. No question, but okay. Then we move on to the next. Thanks, Ivan. The next presentation is online. from Vigo Martinez. We stay in the field of solar energy. So please.
Yeah, can you hear me? Can you hear me?
Yes.
Okay, okay, thank you. Good afternoon, everyone. Sorry for not being there with you today, guys, but promise next time I will. So let me give you a quick review about solar thermal energy facilities that are participating in this nice RISEnergy project. Next slide, please. Yeah, first of all, I would like to very quickly summarize what is the principle of concentrating solar power. We are using just direct solar radiation instead of global solar radiation as the PV technology does. This direct solar radiation reaches Earth's surface in a large amount, as we all know, but with low density, typically in the order of 1 kilowatt per square meter. So what we do at CSP Technology is to use a large area of parabolic or spherical mirrors to concentrate this direct solar radiation into a much smaller area. So this factor of concentration comes from this ratio between the areas. So this flux density of 1 kilowatt can become even thousands of kilowatts per square meter. So this gives us a very powerful tool to apply energy onto processes requiring higher temperatures in the order of hundreds of degrees. Next, please. So the main application that most of you probably know is the electricity generation. This is the CSP, concentrating solar power. This application has been commercial since the 70s of the last century, but with some up and downs. Today, the operational capacity installed worldwide is 6.4 gigawatt electric, and there are 2.46 gigawatt electric under construction. But now we are turning our interest, our attention to industrial process heat. It means the application of this technology to supply heat in the range of several hundred degrees C to industrial processes, like for instance, thermochemical processes. What you see in the picture is an example, is a 1 gigawatt solar thermal system for enhanced oil recovery in Oman, but there are many examples, most of them starting from 100 and something degrees C, typically above the applications we all know as domestic hot water or space heating. Next, please. Okay, so main challenges, well, the equipment used in this technology is exposed to high temperatures and under cycling conditions. So we have to be specific, very, very careful about the materials we use, which must be able to withstand these conditions, particularly for the receivers and also for the thermal storage media. We also need to develop coatings, as you see that there is a field of mirrors exposed outdoor. We need to develop coatings to to deal with the soiling. The soiling reduces the power available. We need to reduce the water consumption at the balance of plant section. These CSP plants mimic the fossil fuel powered plants. The only difference is that we replace a fossil fuel boiler, a water boiler, with a solar boiler. The rest of the plant is more or less the same. You have a turbine, you have a steam generator, etc., etc. So at the condenser, there is a water consumption that we must get rid of. Again, we are mimicking this conventional Rankine cycle, so we use water steam, but we can go to higher temperatures. So we are testing, developing receivers with supercritical CO2 or molten salts, which are more adaptable to our technology. Next, please. As I said, we want to integrate this technology into industrial processes. So we need to improve the modularity and integrability with other energy sources. The modularity has a reason. Normally, for steam turbines, the bigger the turbine, the higher the efficiency. So this kind of plants make sense going to big size. I mean, hundreds of megawatts. We need to develop technologies modular, that you can develop smaller plants, but without compromising the global efficiency. The integrability with other energy sources is also very important. Typically, we have used natural gas to hybridize, but nowadays the hybridization with photovoltaics, for instance, is on its way. And yeah, we need to advance in integrability with conventional industrial processes. What you see is an artist's view of how solar thermal concentrating technology could integrate in a chemical industry park. So all in all, we need to decrease LCOE. We are aware that we need to decrease the LCOE of this technology, and we need to operate in several directions, reduce the operation and maintenance cost, reduce capital cost. At this point, I could say that, well, we are at the beginning of our learning curve because there is not a mass deployment of this technology. So we have a high potential to reduce our capital cost. And last but not least, to improve the reliability and performance. Next, please. Okay, so EU Solaris ERIC is so far composed by Spain, Portugal, France, Germany, and Cyprus. So these are the facilities which are part of, as affiliated entities of RISEnergy. We have CMAC PSA, the University of Évora, the IMDEA Energy Foundation in Madrid, the CENER in Navarra. Next slide, please. 2 clusters in Cyprus. Next slide, please. At the French Pyrenees, the Promé laboratory, the DLR in Germany, and Portugal again, the Laboratorio Nacional de Energía y Geología. And now, quickly, let's review the facilities. Next slide, please. Yeah. This is an aerial view of Plataforma Solar de Almería, that probably most of you know is the flagship of this technology for many years. Here we are offering the big tower, also a thermal energy storage testing facility, and the other facilities offered deal with different salination and water treatment processes. Next, please. Okay, I think we can skip this slide. Yeah. In the University of Évora is offering a very, very innovative molten salt parabolic trough loop, the AMSP, which uses only molten salt for both processes, the energy collection and the energy storage. This is a very, very interesting approach for the technology to increase the efficiency. And also it's offering the Plataforma de Ensayo de Concentradores for testing of small solar concentrators according to the ISO 1806 test. Next slide, please. At the IMDEA Foundation, they are offering 3 facilities: the High Temperature Processes Laboratory for synthesis and characterization of solar materials, the Solar Simulator, which is this device composed of xenon lamps on the left-hand side, and a small power tower for testing of receivers and processes. On the right-hand side, the CENER in Navarra is offering the simulation environment for solar energy systems, relying on an open source software, which is Tonatiuh, and a CST library developed on the basis of the Modelica. Next slide, please. Sorry, this is repeated. Let's skip this. In Cyprus, we have two very interesting facilities. On the left-hand side, I'm talking again about the integration with other renewable sources. PolyRes is able to test, validate, and demonstrate in operational working condition poly-renewable energy systems, integrating with solar thermal, photovoltaics, wind turbine, stirling dishes, and also with energy storage systems. It's a very interesting application. And on the right-hand side, the Proteas, which is let's say, a typical power tower facility for the testing of receivers and applications. Next, please. Also, we have another flagship in the European landscape, which is at the French Pyrenees, the Promet facility from CNRS, with the Themis tower. On the right-hand side, the largest solar furnace in the world, the megawatt solar furnace, able to reach up to 3,500 degrees C for several applications on material specifically. Next, please. And also small solar furnaces for materials treatment for the study of advanced materials. And the microsolar, which is a small parabolic trough system to study different components. Next, please. DLR is offering the largest solar simulator in the world with 300 kilowatt power. And on the right-hand side, they are offering these two towers. The tower on the left side is a full energy production, full electricity production system in itself. So you can test a solar receiver and you can go to the final step of generating electricity with this system. Next, please. The other tower, the tower on the right-hand side, has three testing rooms and is able to test several experiments at once in the different levels. The solar field on the right-hand side has 2,000 heliostats, which delivers power to any of these test room in these two towers set. Next, please. And last but not least, the Portuguese partner, ELNEC, is offering also a solar tower for testing of receivers, a high-performance computing cluster for modeling of computer fluid dynamics, particularly for the working fluids in solar applications. Next, please. And the last facility they are offering is the Laboratory of Solar Energy, where you will be able to carry out optical characterization of both reflectors and absorbers, work on measurement of solar radiation, and also the testing of solar collectors. That is the collection of facilities we are offering for access in the CSP STE community for RISEnergy. Thank you. Thank you very much for your attention.
Thank you, Diego. The idea here is that we should not go into a deep discussion because we have a final discussion round after all presentations foreseen. Just if there is an urgent question to Diego. Yeah, Philip.
Okay, yeah. Just a quick question. Do you have any links to the very large project in Ouarzazate, and directly or indirectly?
Not yet. I know some of my colleagues here in Almeria have colleagues from Warsat participating actually in European funded projects. But it's not the case of EU Solaris. EU Solaris eventually, I mean, Morocco could eventually join EU Solaris if the case is considered.
Okay. And thanks, Diego.
Thank you.
And we move on to the next one. We leave the sun and we go into the water. Is this right? Jimmy Murphy? It's also online. Okay, I hope it works.
Good afternoon, everybody. Just to make sure everybody can hear me okay?
Yes, fine.
Perfect. That's great. So my name is Jimmy Murphy and I work in University College Cork and I lead the RISEnergy preparatory project, which aims to set up an ERIC with respect to offshore renewable energy infrastructure. So just to start my presentation, I will talk a bit about the terminology because sometimes there's a bit of confusion, sort of with the different terms that are used with respect to energy that we get from an offshore environment. So what we use in this project and what defines the infrastructures associated with me and the other partners is ocean energy, but other more generic terms are used such as offshore renewable energy, which people are aware of, and marine renewable energy. So I'll start with the most broad term is offshore renewable energy. That sort of refers to energy you get from anywhere in the offshore environment. So you see from the list below there's a number of different sort of sources of offshore renewable energy. Marine renewable energy then refers to energy that you get from the water. So that cuts down, it really cuts out, sort of offshore wind and offshore solar energy. And then when we come to this project here, what we're referring to as ocean energy, and what we generally mean when we talk about ocean energy is wave energy and tidal current energy. So this project and this section here, or sector, is focused on infrastructures that can develop wave and tidal energy technologies. However, sort of a lot of the infrastructures as well are relevant to offshore wind, particularly floating wind, and they do a lot of testing on floating wind technologies and also floating solar, so we can test new platforms for demonstrating solar energy in offshore environments. So if we can move to the next slide, please. Okay, so just looking at the wave and tidal energy sector in general, sort of why we want to develop it is because it's regarded as being complementary and a more dependable source of renewable power than wind energy. That's what the protagonists say about wave and tidal energy, sort of, and to a certain extent that is true. Tidal currents, sort of are very predictable. Sort of if you know your tidal currents and you measure them, you can predict them, sort of decades in advance. So you can determine the amount of power you're producing at any point in time, sort of, because you have that knowledge of currents, and it's not weather dependent. So that's a particular advantage of tidal currents, is its predictability, and that it can feed in and balance out other types of renewable power. Wave energy then is regarded as, sort of, waves that are generated by winds, but they're not totally dependent on the wind, because waves can travel, across oceans, so they're not dependent on the local wind conditions. So, between waves and tidal currents, sort of you can get a broader spectrum of energy, so you're not relying on the wind blowing the whole time. So that's the particular advantage of wave and tidal energy. However, the disadvantage is, sort of that you're putting technology into a very severe environment, sort of, and that makes the development process and the survivability and the reliability of technologies, sort of difficult to achieve. So if we look at where wave and tidal energy are at the moment, sort of tidal energy has progressed to small scale tidal farms, sort of, whereas wave energy is primarily single unit demonstrators. The EU have a target of 100 megawatts of wave and tidal energy by 2025, and it's almost certain that we won't meet that target, along with the 1 gigawatt target there is for 2030. And a lot of that is to do with the difficulty of installing and operating these technologies in these extreme environments. There's also issues such as consenting and financing and marine spatial planning that are associated with these technology developments as well. So if we move to the next slide. I've just listed the challenges here, sort of that are particularly hindering the wave and tidal energy sectors. First of all, is the high levelized cost of energy, and sort of that they're not being competitive with offshore wind. Sort of offshore wind started off at a relatively high cost, but because of the scale and the pace of development, the costs have come down very quickly. Wave and tidal energy are not given that chance to develop as offshore wind has been given. So in many of the auctions that are released by different countries, wave and tidal are put in direct competition with offshore wind, and they cannot compete, so they fall behind as a result. Another problem with wave and tidal is the difficulty in scaling to offshore wind unit size. So a typical wave energy device is less than a megawatt. A tidal current device would be a megawatt to 2 megawatts. So you need to put a lot of them out there to get the same amount of power as you would from a typical wind turbine. Now, an offshore wind turbine can be 15 megawatts. So you could have sort of say, you could have 30 wave energy devices for one wind turbine. So obviously that's an issue. You can't scale up to the same size as you have with offshore wind. And the next one then that I mentioned there is the extreme environments. If you look at the picture on the right-hand side, you look at sort of 50-year return wave heights for the west coast of Ireland, and you can see you get wave heights of up to maybe 18 meters. And they're not even maximum wave heights. So you generally can get maybe up to 30-meter maximum wave heights, in the environments you want to put these technologies into. And that obviously is a significant challenge if you're trying to install devices, operate devices, or even maintain devices. Can you get out to these during extreme conditions? And when you have components, mechanical components in the water, that it's very hard on them in terms of, sort of reliability. So that's part of the challenge. The last challenge then is the lack of convergence of technologies, so there's a lot of different options there, and, sort of ways of generating power from waves and tidal, and we haven't converged in the same way as we have for offshore wind. So we move to the next slide. So this slide is sort of to explain a bit the type of infrastructures that we have in the RISEnergy project. Sort of because development of wave and tidal energy requires sort of an incremental approach where we scale up. Sort of it's all about scaling, where we start off at very small scale devices in laboratory environments, and we gradually build up then to a full scale device deployed at an offshore test site. So the range of infrastructures that we have within RISEnergy combine all the requirements to take a technology from stage 1, as you see there, which is TRL level 1 to 3, so up to stage 9, which is sort of an economic validation of the concept itself. So in the two pictures you see on the right, the top one there, you can see a wave energy device being tested in a wave tank. And in the lower one, then you see a tidal energy device, sort of in an offshore site, sort of after being deployed. So in order to understand and to ensure that the technology has been properly de-risked, sort of that it has to go through all these stages. And I suppose, sort of technology spend a lot of time in the laboratory environment because that's what costs the least amount. Once you go offshore, you're talking about millions in terms of deploying a technology. So that is a real burden on developers who generally don't have much funding. So that's why a lot of developers look to programs like, so in the past we had MARNet 2 that gave transnational access. Now we have RISEnergy that to give them more scope to be able to deploy and develop their technologies. So if we go to the next slide, please. So before I talk about the actual technology or the laboratories and research infrastructures themselves, I just mentioned RISEnergy and what it is. You know, sort of RISEnergy is a sort of a distributed research infrastructure. You know, sort of that reached the S3 roadmap in 2021, and brings together, you know, sort of laboratories and offshore test sites for developing, you know, sort of offshore renewable energy technology. So we include wave, tidal, offshore wind, and floating solar as part of our group. So as part of RISEnergy, we have a lot of the infrastructures that are present in RISEnergy, you know, sort of that I'll be explaining in a minute. And, you know, sort of just to show you the countries that are signed up to RISEnergy at the moment are Ireland, the UK, Belgium, Spain, Netherlands, and Portugal. And we have other countries as well that are progressing to being involved as well. So our vision is to be established as an ERIC by 2026, 2027, you know, so that's our timeline. So the next slide, please. So I just talked through a few of the infrastructure. Well, I'll go through all of them, but I'll give more detail on others, you know, sort of to indicate the different types of infrastructure that we have as part of RISEnergy, and how they incorporate what's required for developers in this sector. So if we look at the top three infrastructures there, you know, sort of their test tanks, you know, sort of, or, you know, ocean basins, as we call them, that can reproduce wave conditions, ocean conditions in a laboratory environment. So we can scale down, you know, wave conditions measured out in the ocean or input in synthetic conditions and run them against a scale technology. So that's what those three facilities at the top there do. You know, sort of the one on the right-hand side, you know, center in Rome, you know, sort of they're a towing tank, so they're more suited to tidal energy technologies than wave energy technologies. The bottom three there, you know, sort of El Bocal in Spain, you know, sort of tests for corrosion, so you test materials for the marine environment. Plocan is a full-scale test site in Gran Canaria, you know, where they've tested offshore floating wind and wave energy devices, as well as components and other devices. And Technalia then is a platform for testing materials, components in an offshore environment. If you go to the next slide. Just showing some of the other infrastructures there, you know, where I run the Lear National Ocean Test Facility, which is in University College Cork, and we have a series of test tanks and test rigs for developing technologies at low TRLs, you know, before they go into the offshore environment. The Ephemer tank there is a very specialized tank for testing tidal energy devices. It can run both waves and currents in the tank, and it's been used significantly or quite a lot to test tidal energy technologies. If we move to the next one, please. And this VGA lab in Italy, it's a fairly new facility, and it's for testing power takeoff and loading of components on wave energy devices. So if we take the power takeoff first, you know, sort of, you can't really test the power takeoff system in a test tank. So you do it in a dry lab first before you go offshore. You want to make sure that your power takeoff system will work efficiently, you know, so you can't do it in a wet environment, but you do it in a special facility like that. That's in Italy. And the last one there is the University of Ghent, you know, Coastal and Ocean Basin, which is a brand new facility, you know, sort of in Ostend, you know, sort of that's used for testing, you know, sort of it can test wave and current and floating wind technologies. So if we just move on to the last slide, please. And these infrastructures here, I was told they weren't directly in the ocean energy, but they all relate to ocean energy. You know, the first one there is the Gross Welland Canal, which is in the University of Hanover, which is it's a really long wave tank, 300 meters long, and it's 5 meters deep, and it can generate really high waves. You know, so it can test a variety of renewable energy technologies, and it has just been recently revamped for over 30 million euros. You know, so that's a state-of-the-art facility. The University of Edinburgh Fast Blade is for testing blades, you know, particularly tidal turbine blades, sort of fatigue and loading, and looking at new materials and their behavior. The University Strathclyde is a big long wave tank or test tank for testing wave energy and sort of tidal energy technologies. And the last one there, sort of is EMEC, which is the European Marine Energy Centre, which is sort of I suppose the most prominent offshore test site in the world, and it has tested more technologies than any other site in the world. So we're very lucky to have that facility as part of our offering as well. So that covers everything in relation to ocean energy. So I'm happy to take questions now or later.
Thanks. Thanks, Jimmy. I have noted something for the discussion later on. Is there any urgent question to Jimmy now to these installations? Then I would suggest we move on. Thank you, Jimmy.
All right, thank you.
The competitor you mentioned will come as the overnext talk, but first we go on land to the biofuel and bioenergy system. So please, Berend.
Yes, thank you. My name is Berend Vreugdeneel. I work for TNO and I'm part of ERA Bioenergy. The topic is biofuels. Where do I point? Okay, so maybe a little bit different than the energy applications. If you talk about primary energy use, you have electrons and you have molecules. And I think at least several years ago, the share of molecules was about 80% in our primary energy use, which is very difficult to replace, but bio can be a useful source there. And what I try to show in this picture is a little bit a schematic overview of what you can do with biomass. So there's several pathways of converting biomass into useful forms of energy. It's either thermal or it's biological. It's extremely flexible. I put at the bottom a few pictures of biomass, and you can think of manure, you can think of digestates, seaweed, but also lignocellulosic crops, agro residues, municipal solid waste. So it's very diverse. It also means that the technologies that you use to convert them is very diverse. The two nice things with biomass usage is that you can link it with hydrogen very nicely to increase the output of your desired product and valorize more of the carbon in the feedstock. If you're not capable of doing that, it's also an option to generate negative emissions, either through biochar production or through CO2 sequestration. The back-end applications are also, again, very versatile because you can go to gases or you can go to fuels. The most common ones are digestion of manure to produce biogas, and from biogas go to biomethane. Another one is the fermentation of sugars to alcohols. Those are what I would say already more advanced. But the challenges are that we need to focus on these new feedstocks, these different feedstocks, and that's a big challenge. Also, the ambition of the EU on biofuels is quite large. For instance, by 2030, they aim to produce 35 BCM of biomethane coming from digestion and gasification. Currently, we're at, I think it's just above 4 BCM. So there's a huge gap in the coming 6 years to be closed. So that's one of the main challenges, I think, with biofuels, is that we want a lot, but there's not yet a lot available to reach this. So the challenges that I pen down is that, first of all, we need to investigate much more feedstock. So you cannot use all type of feedstocks. So you have to respect land use, you have to respect food, biodiversity. So certain feedstocks are out of the question, which means that you have to investigate new feedstocks. Also, new crops are grown, and then you have to know, how does this behave in my technology? So there's a lot of upfront knowledge to be built up with respect to feedstocks. Then if you go to building your pathway to a fuel, methanol or Fischer-Tropsch or methane, then it's all these steps, they need to be linked, and that needs to operate like a machine. It's not just a single step, it's the feedstock pre-treatment, the feeding, the conversion, then the cleanup, and then the production of a fuel, and then going to product specifications. So this is very complex and challenging. And the last one is also that back-end applications. If you think of the way that we used to produce, for instance, Fischer-Tropsch products or methanol, it's based on fossil fuels like methane, coal, oil, and they're all abundantly available. You have point sources, so it's easy to build up an installation, go to very large scale, have economy of scale. If you think about biomass, well, it's very diverse, and it's all over the place. So you cannot really go very easily to very large scales. So you have to rethink your back-end applications. This means you have to do technology development there. Maybe some catalyst needs to be changed, solvents for cleaning, etc. So there's a lot of development issues. So within our biofuel transnational access, we have 6 offers. There's also one international from NREL, but that will be presented later. We have Lenec in Portugal. We have Tubitac in Turkey, the Netherlands at TNO. We have Record in Italy, and we have DBFZ in Germany. And I think through these 6 or 5 organizations, we cover virtually all possibilities of going from a feedstock to a fuel. So some details about these, what's on offer. For TNO, what we put in is really the gasification platform as a starting point to convert feedstock, biomass feedstocks into gas, do the whole cleanup, test new catalysts, new sorbents, new liquids, and then go to fuels. And that's up to high pressure conversion. So we can do up to 100 bar, methanol, Fischer-Tropsch, etc. And also supporting this with extensive analysis. For Lenec, they have the biomass and bioenergy research infrastructure, which is actually covering many different topics. So it's microalgae biorefineries development, where you can look into CO2 fixation, going all the way to biofuels, but also how to deal with wastewater, because this is a wet biomass. They also offer thermochemical pathways like liquefaction, pyrolysis, where you produce liquids, which you can replace fossil liquids or maybe upgrade directly to fuels, and also gasification. Another topic what they look into is biomass deconstruction, so breaking biomass down in more simpler molecules, using various approaches, high pressure ionic liquids, and they also have fermentation of sugars. And this is not the first generation sugars, but sugars that you obtain from lignocellulosic biomass, which is C5, C6 sugars. So all these different pathways are included. DBFZ, they have 2 different topics. You can see a nice picture of a biogas plant. But this is for anaerobic digestion processes, where you convert, for instance, manure into a biogas, and then you can upgrade it into methane, which subsequently you can go to LNG or do other things with. But they support you with all the downstream equipment and analytical techniques that you need. The second thing on offering is the hydrothermal processing and biomass disintegration unit. Disintegration, again, it's breaking down of biomass. They offer several batches going from small scale applications to up to 100 liter units, and temperature ranging between 150 350 degrees C. So that's already quite severe. And they help you from proof of concept to an experimental scale-up of carbonization technologies, liquefaction. So that's where you either go to biochar or go to liquids, or completely destroy the biomass with biomass disintegration units. And again, extensive analytical options. And I think that's for all research organizations, the analytics are really dedicated to the work that we're doing. So that's also good to have. Tubitac is offering a fluidized bed and fixed bed pyrolysis and gasification setup. So this is more thermochemical conversion, higher temperatures where you go to liquids or to gases that you then can further upgrade into fuels. They support you with an analysis department as well. And a Record in Italy, they have a thermochemical experimental facility for producing liquids, so hydrothermal liquefaction, and slow and intermediate pyrolysis, where you also produce biochar. So that's also the option there to investigate the quality of the biochar through chemical leaching and testing of fuels in micro turbines. So these 6 TAs that are on offer, they really cover the whole scope of different feedstocks. So you can use wet feedstocks, and you can go to the partners, you can use dry feedstocks, and there's other partners, but they can all help you to convert a given biological residue and convert it into a biofuel.
Oh, yes, thank you.
Okay.
So there's already a link shown to chemical energy carriers in the storage area. Now we move to the competitor of the previous presentation, offshore wind. Is presented by Julian Balzen, is that right?
Yeah. Thank you. I think a lot of people are a bit surprised to see me because I'm not a scientist. So, but I think, well, as I understand, maybe Anthony Fraisse is online from DTU, my dear French colleague. So maybe he can support me if I say something wrong or something not really precise. So please be indulgent with me. So offshore wind. So I think I need to use this. Yeah. And it's the pointer, perfect. So let's back a little bit behind. So take some history. In 1991, the first offshore wind turbine was built in Denmark, which was quite a groundbreaking project at the time. 1991, well, I think it's 33 years ago right now. So maybe some of you weren't born. No, I think yes. I was born too. And it did well. It was a groundbreaking project, and it was well. Now it's a dismissed wind turbine, but well, it was really a learning experience for the offshore wind industry, and to highlight the need for maybe larger and more efficient turbines and improve the maintenance strategies to ensure the long-term viabilities of offshore wind. So it was 11 turbines consisting in 5 megawatts. So it was quite a small-scale project at a time. And afterwards, after the dismantling of this offshore wind turbine in Denmark, the blade was tested to assess the performance and the structural integrity, and indeed, it was discovered that the blades were significantly over-designed. Indeed, it's meant that they were built to support higher load and stress than necessary. And it was result, indeed, from quite maybe limited knowledge about the offshore wind condition at the time. But now, indeed, the knowledge have been improved. And for example, for the location of offshore wind, there are, the North Sea is known for this abundant wind resources and an ideal location for offshore wind development. It's a large space for the construction of offshore wind, which is quite important. The fact that, well, they have not really a significant environment and special constraint in North Sea. And as you can see in the graph here, the countries bordering the North Sea, so UK, Germany, Norway, Netherlands, Denmark, and Belgium, have really great ambitious plan, as you can see there, for to meet their renewable energy target. So it's 261, I don't know if you can see it on the graph, gigawatts for 2050. The fourth one, well, we have 2 types of offshore wind turbines. Well, the first one is the most known. It's the bottom fixed offshore wind. It's the most common type of offshore wind installation. So the turbines are ensured to the seabed using foundation and using, you know, large turbines in bottom fixed offshore, increase the efficiency and the cost effectiveness of offshore wind farms because you maximize the power output per unit on the seabed area. And well, advances in turbine technologies such as, you know, larger rotor diameters and taller towers enable the deployments of larger turbines and further enhancing the performance of bottom-fixed offshore wind project. We have also quite a new technology, well, new several years ago right now, the floating wind technology has been rising up. And well, the floating wind technology involves turbines that are not fixed on the bottom of the seabed, but instead they are attached to the seabed by mooring lines. So floating wind turbines have the potential to access deeper water, opening up new area for offshore wind, so maybe larger areas to be installed, and whereas sometimes bottom-fixed installation are not feasible. And floating wind also break the size harm height race amongst turbine manufacturers by offering a more flexible and scalable solution that can be deployed in a diverse marine environment. And at the end, well, for the state of the art, we have the hydrogen transport, which is 8 times cheaper than electricity. Hydrogen was a promising energy carrier for storing and transporting renewable energy. And well, there is also an advantage for the cost. So the cost of transporting hydrogen by pipelines is often significantly lower than transmitting electricity over long distances, especially when, you know, offshore wind farms are located far from the shore. And by converting also offshore wind energy into hydrogen, like electrolysis process, the excess of renewable energy can be stored and transported efficiently to mainland lands for a lot of applications, just like heating, transport, and industrial processes. So it was the state of the art, but now, oh, the next one. Yeah, we have a lot of challenges, particularly the question of the size that I mentioned before. So are larger turbine the answer of you know, matching all the challenges that we have right now? It's an interesting question, and it's not really easy to say yes, because how to scale up manufacturing and installation sustainability with larger turbines? To scale up turbines manufacturing, we have also to improve manufacturing processes, optimize supply chains, and of course reduce material waste. And for that, the collaboration between stakeholders and governments can facilitate the development of standardized component and streamlined manufacturing technique. Second one, the installation for offshore wind farm with the larger scales. Has turbine size increased, the logical challenges associated with the installation increase too. So we need to find innovation in installation methods, for example, advanced vessel technology, automated assembly processes, and initially, for example, investment in port infrastructure will be important, and also skills for labor training to support the growing offshore wind industry. Larger turbines have lower LCO. Well, that's a debate. For when you calculate for mathematical point of view, you can say yes, because well, when you have larger turbines, you can make a lot of economies of scales and optimizing the balance between turbine size and site-specific condition. But some specialists say that well, it's more a question, it's more conjecture right now, and the answer it's not really easy to give. Also the unknown terrain for wind and materials, because offshore wind projects often encountered unknown seabed condition, challenging weather pattern, and corrosive marine environment. So you need to use advanced materials with high corrosion resistance to ensure the long-term viability of offshore wind infrastructure. The fifth one, how to build and connect also floating wind turbines, because building and connecting floating wind turbines require innovative engineering solution for anchoring, mooring, and electrical connection. So we need also to regulatory bodies and research institutions to develop standardized design, installation procedure, and safety guidelines for floating wind farms. The sixth one, so the alternative turbine design. So we can also explore alternative turbine design. We know, for example, airborne wind energy system or vertically axis turbines, multi-rotors, etc. can also offer advantage in terms of scalability, efficiency, and environmental impact. So all this kind of disruptive technology could be also a solution. The grids and the energy system integration. So integration of offshore wind energy into existing grid needs a careful planning and coordination to ensure the stability and the reliability. And advanced grid management technologies such as smart grid system and energy storage solution can also facilitate the integration of renewable energy resources like offshore wind. The grid connection versus hydrogen production. Well, we can say that this kind of debate, grid connection and hydrogen production, really should be evaluated according to the economic and environmental feasibility of each option based off the local condition and the energy market dynamics. And last but not least, well, the coexistence with the other sea inhabitants and users. So offshore winds development must consider also the potential impacts of marine ecosystem and other users of the sea, so just like, for example, fishers, shipping lanes, recreational activities. So conducting comprehensive environmental impact assessment, engaging with stakeholders, implementing mitigation measures can minimize the conflict and promote coexistence between offshore wind infrastructure and marine habitats and marine users. So, having saying that, well, the five infrastructure have been selected in the project RISEnergy for offshore wind. So I talk a lot about North Sea, but well, not all these five infrastructure are located in the North Sea indeed. We have one, for example, in Greece, or the one from Cress, which is a 100-meter mast with leader. So it's a Mediterranean Sea. We have one in Nantes in France, which is a climatic wind tunnel, but I think it's explained here. So the one in Nantes is can simulate a lot of climatic conditions, so -32 to +55, rain, snow, sun, etc. So that's really interesting. It's really impressive too, and it's located in Nantes, so near the Atlantic coast. The second one that I have the chance to visit is the DTO Material Lab. So it's more into the materials. It's quite impressive because, well, it's kind of fibrous content measurements, optical microscopy. So we are really dealing with materials. The third one, so I talk about it. It's the one in Greece. So it's a 100-meter. It's quite impressive too, with a mast with leader. The fourth one is based in Sweden, in Chalmers. So this one is a wind turbines with variable speed. And the last but not least, the one based in the Netherlands, powered by TNO, which is a scale hybrid power plant test facility with wind and solar. And I don't want to announce the coffee break, maybe. So maybe if you have questions. Thank you.
Thanks, Julian. I think in all presentations, there were already keywords coming from the system to the materials, aggressive environment, harsh conditions. I hope that you can were all able to make some connections to some of the things and also learn something new. Now, between us and the coffee break is only one thing, that is a group photo we would like to take. Before you leave the room to the coffee break outside, I would ask everyone to come up to the stage here and we make a group photo. And then we come back at, I would say, 1:15 according to schedule.
sort of materials for the hydrogen technologies, both on the usage, storage, and the production. And the other part is that if you want to make hydrogen competitive, you have to go outside transportation only, and you have to look at some industries that are inherently difficult to adopt new sort of fuel, including hydrogen. So these are the problems. So you're dealing with a sector that is already producing what you want to produce in a decarbonized way, in a much cheaper way. So we're looking at less than $1 or euros a production of the hydrogen that comes from sort of hydrocarbons directly, or capturing of CO2 as part of that, making sort of blue hydrogen and so on. You're looking at increasing of the price of the green hydrogen from less than €1 per kilogram all the way into 9. So it's a very a few of those. So one of the issues that is, of course, important is the cost, and the cost is not just because of the sector that is going to fit, is about the competitiveness of the technology itself in those sectors that we have to look into. Transportation cost of hydrogen is 2 times more than sort of natural gas, so it's pretty high in that sense. So storage technologies is also another sort of elements of the hydrogen technologies that has to work with. And then use cases outside transportation and renewable firming, it's something that also is challenging in terms of the competing with the conventional technologies and fuels. Okay. Okay, so I want to bring an example that is started by the World Bank. I like the way that the key numbers is talking about this. So in a very simple term, if you want to produce 1 million tons of hydrogen, you need about 10 gigawatts of the electrolysis. And I'm talking about the green hydrogen. Because of round trip efficiency of the system is about 50%, that means you need 20 gigawatts of the renewable powers to basically generate that, right? And then if you have the cost of this electricity in average, it's going to be about $30 billion or euros in that sense, if you put them at the same sort of level. So if you have a project you want to run for 20 years, right? Just multiply everything to 20 years. You're looking into sort of this 30 billion is a lot of money, right? I mean, one single enterprise is not able to put a lot of that money in. So therefore, you need, of course, investors. There has to be some return on that. So 30 billion divided by 20 billion, which is 20 times of 1 million ton per year, you're getting into $1.5 per kilogram. And that's what everybody thinks that the cost of hydrogen would be at the point that we're going to get into. But the reality is that if you add markup of the investors who bring in that $30 billion and the O&M costs, the operation and the maintenance, we're getting into $4 per kilogram. And if you compare with the willingness to pay, which is at the minimum of 9 to 10, as I said, you can buy hydrogen at less than €1. So 9 is too much. You only have 100% sort of markup, which is about 50% margin. So it's not huge competitive compared to other sources. And this is a big problem that we have to address in terms of the cost of materials and doubling of the production. And to tell you the truth, the way to do it is all through materials and the accelerating on that. And that's where the hydrogen technology is basically focusing on. So in terms of infrastructure that we have in this project, so a lot of that is from our organizations in Germany, and also 2 infrastructure in Italy. So we have infrastructure in Rotendale in Italy is focusing on the syngas and production of hydrogen. I talked about that a little bit in terms of the purification facilities and the testing facilities there. The Green Hydrogen Lab as part of CNR also is doing different sort of level of testing at the stack level as well as at the catalyst level and so on. And then at our facilities in Germany, some of the facilities that we have is part of our sort of living lab energy. This is part of the ICT sort of a stream in this project, but it's also heavily powered with the hydrogen facilities that I talk about that a little bit. We are building also sort of accelerated robotic systems that are able to test new materials, specifically on the non-fluorinated materials. As I said, is going to be a big hurdle for the industry to deal with in the next couple of years. And some facilities as virtual for the data augmentation and testing data that would be useful for supporting a lot of these activities. Okay. So a few words about some of the facilities in Italy. So as I said, on the syngas side, we have facilities that produce up to 40 kilograms of the hydrogen of each feed, facilities for testing different catalysts, purification of the hydrogen, testing that and all that, which is extremely important for the production side of the hydrogen. And as part of CNR in the facilities in ITEA, in Advanced Energy Tech Institutes, it's more focused on the testing sort of stations, starting from 5 kilowatt system, maximum power at the 200 amp of the maximum current. These are typically a size of the hydrogen production for maybe few of households, if you want to just compare to the actual numbers. If you talk about 1 megawatt or 2 megawatt or up to 10 megawatt, we're talking about a city of 300 people or 300 families. The electrolysis can connect to the renewables in that sense, and the scale-up facilities also is part of that as well. The infrastructure in Jülich is pretty unique in a sense that the footprint of investment is huge in this region that I come from. So this region has seen investment of 1 billion euros in September 2022 to convert all the coal mines of the region into hydrogen production. So we have facilities are built as we speak on the production and storage. The LHC is a technology of storage that is mainly focus of these facilities. So as I said, the living lab is also part of the infrastructures in the ICT, which I'm sure is going to be spoken about in the next few talks. But the importance of this is basically facilities that are able to test hydrogen. So we have testing hydrogen up to 300 kilowatt, which is one of the largest testing facilities out there. And then we have also developed robotic labs to be able to test and accelerate the production of the hydrogen using non-fluorinated sort of membranes. As I mentioned, by 2030, industry has to get rid of these type of materials, and therefore there's a lot of activities and that is going on. So this facility is still in building. We are building this in form of some robotics that are able to optimize inks that are built out of sort of Nafion materials, and therefore be able to predict and formulate new type of the inks, which is the heart of the running of the systems at highest sort of capability of the production of hydrogen. This facility, as I said, is built, and eventually the end user is able to formulate few things and send the requests and basically build and test some of the ink materials. And the last thing I want to talk is the virtual facilities that we have built since 2021. It was part of also other project. The way this facility essentially used to work was to be used as a sort of virtual environment for visualization of the data from different testing for different purposes. So initially it was used for the education purposes. People go there and basically communicate on certain data and visualization. And then we saw industry needs on visualizing of the industrial sort of testing. For example, if you do a stack level testing of using new materials, you should be able to basically sort of augment the testing data in real time into the near sort of at the edge of the technology. And that's what we have basically moved a little bit of focus on the on the testing data, and we got millions of data from industrial partners to put sort of visualizations into the virtual rooms. And with the facilities that we had, we were able to augment that into the actual device. This is extremely important. There is no model or the digital twins added yet. It's just visualization of the data itself. So if you're sitting beside a facility of the 200 cells stack of the hydrogen, you don't see what's going inside it. But if you sort of visualize data, you can see which cell is vulnerable into certain sort of vulnerability of the testing. So you can basically get insight right away. We are improving that and upgrading that with the new technologies, but the focus on that would be more on the running of the virtual sort of data on top of the equipments, which is important for the failure analysis, failure mode analysis, and also monitoring in the testing facilities in industry as well. And thank you very much.
Thank you, Kourosh. I think we have to move on because the last hour is quite tight with 4 presentations. The next field is broad. It's energy storage, and Miriam will tell us what is inside.
So good afternoon, everybody. My name is Miriam Gil Barajia. I also work at KIT, and I am the coordinator of the ERA Joint Program on Energy Storage. My role in RISEnergy is I will be coordinating the work package on project coordination and management, but also I will be leading the field of energy storage and the research infrastructures covering this field. So I hope it works. Okay, it works. Let's talk about the challenges. I will look there. So one of the most urgent challenges of the energy system today, I would say, is to minimize curtailment and to maximize the renewables utilization and integration, right? And energy storage is one of the main pillars to achieve this, because not only for electricity, but also heat or other energy vectors, is the only possibility to integrate renewable energy in a system-safe way into the energy system. And what we need is to secure our energy needs in the different sectors: transport, residential, and industry. And if we have a look at the state of play, we can say that batteries will certainly solve the problem of transportation. Electrification of this sector is very much advanced. There will be, for sure, other technologies that can help, for example, hydrogen or fuel cells for specific applications. But this is a sector that is more or less solved now. But it's not the same for residential applications. So indeed, batteries can help to solve this problem, but there is still the problem of heating. And the same for industry. We don't know how to solve this problem now, because one of the biggest challenges nowadays to achieve the clean energy transition by 2050 is the seasonal storage, long duration seasonal storage, which means we don't know how to save the energy for the winter, because so far we have been using fossil fuels. And this has to change if we want to decarbonize Europe, right? And if we have a look in the energy storage technologies, they can help us a lot to achieve this goal. And you can see here, depending on the storage principle, we have different energy storage applications. For example, electrochemical energy storage, batteries, a very, very large portfolios of batteries that we have already. There is also chemical energy storage, like power-to-X, e-fuels, hydrogen, ammonia, reactive metals. We also have the possibility to store energy, like thermal storage, heat, phase change materials, molten salt. We have mechanical storage, like pumped hydro, compressed air energy storage, liquid air energy storage, flywheels, and so on and so forth. And we have also electrical energy storage, like, for example, superconducting magnetic energy storage or supercapacitor. But as you can see here, we have many technologies available, but if we take into account that the future energy system will be much more decentralized, disaggregate, and multi-vector, you can see that there is not only a single technology that can solve all these problems and all these applications. So In some cases, we will need a combination of them. And this is what we call hybridization for energy storage. And as you can see here, it's the utilization of 2 or more energy storage technologies together in either a system, device, or material level to provide technical and economic advantages beyond what any single energy storage technology can provide. And this is what we are looking at the storage project. It's a research infrastructure project in the field of energy storage. And the key priority of this project, research priority, is to find hybrid solutions for the different applications that we have in order to store energy. And this project is already ongoing, and you can see here more similar are the ones you have in your own field. Let's have a look how we address that within RISEnergy. We have here the 6 different energy research infrastructures on dealing with energy storage that I would like to show you now in more detail. We have 2 of them dealing with electrochemical energy storage. The first one on the left side is from KIT, HIU, Helmholtz Institute Ulm in Germany, mainly dealing with batteries, all kinds of batteries, assemblies, cell component characterization. You can do pretty much there, all related to batteries. And we have another one in the Czech Republic, Thomas Bata University, more focused on lithium-ion batteries, and they also can provide some life cycle assessment and socioeconomic aspects of this kind of energy. The third research infrastructure that I would like to show you is dealing with chemical and electrical energy storage. It's based in the University of Perugia in Italy, and in this case, they have test bench for reactive metals steam oxidations for hydrogen production, for example, for reactive metals like aluminum, but also they have other activities in fuel cells and power to X. Then we have 2 additional research infrastructures in the field of thermal energy storage. The first one is situated place in Messina in Italy, at the CNR, and it's called the Center for Thermal Energy Storage and Conversion Technologies. And as you can see here, you can also perform some characterizations from materials to system level or many other experiments. In addition to this one, we have another one in Karlsruhe at KIT called Karlsruhe Liquid Metal Laboratory. And this is a test of a first of its kind heat storage system with liquid metal loops for hydrogen production from methane or biogas up to 100 degrees, for production of solid carbon and oxygen from CO2 from air, for example, and many other kind of experiments. And the final research infrastructure that I would like to show you today, it's situated in University of Padova in Italy, and it's mainly dealing with fluid mechanism and energy system. You can see here, you can perform different experiments of hydraulic machines and also some conditions and cavitation behavior of Pelton turbines and hydropower and other energy storage technologies. And in this case, if you have questions about this technology, you can directly ask Giovanna because she's here and will answer all the questions regarding this technology. It's the only one that is here today, so from the energy storage side. Okay, that's all. Thank you very much for your attention. And if you have any questions, just let me know.
Thanks, Miriam. As you see, we are leaving now the field of individual technologies and spanning a little bit broader. And the next 2 presentations are also related to grid and communication. And Thomas Strasser will present the integrated grid activities.
Thank you, Peter, for the introduction. So it's also a pleasure for me to be here at the kickoff meeting of RISEnergy. I'm Thomas Strasser from the Austrian Institute of Technology. And it's my pleasure to give you a brief overview of what's happening or what we can offer from the grid side. As Peter already said, we saw a lot of different technologies, generation technologies, storage technologies, but they are very important on the one hand side. On the other side, they are made also for us customers. So we need to bring the energy to the end users. And here the grids come into, especially the infrastructure comes into place. So we are talking here in this field about the energy infrastructure. So mainly the electrical grids, but not only. We have to deal with the planning and the operation of the electric of the energy infrastructure in general. We have on the one hand side what we have already seen, large-scale integration of renewable energy sources, PV, wind, and other types offshore renewables, for example. On the other side, we have also to deal and to integrate the consumers, the customers, the loads. Here we see a lot of the developments on the storage side. Electrification of mobility has already been briefly mentioned. This is also interesting field that influences the operation and the planning of the grids. Flexible loads like heat pumps and so on. So we need to, as you can see here also, to integrate all different kind of generators and consumers. We see the electric energy system as the backbone of our modern society, but not only, it's not only the supply infrastructure, there are also other types like gas network, heat network, and so on. So nowadays we are looking more into an integrated system. You need a lot of different automation, control, communication, ICT approaches. So nowadays we call it also a so-called cyber physical energy system. And we cannot analyze the individual areas independently. When we always look at the infrastructure itself, then we always see it from 3 different angles from the system point of view. Here we have different challenges, urbanization, aging infrastructure, electrification of mobility, and so on, distributed generation. But we have also lots of technologies that we need to integrate from the technology side. Power electronics plays an important role in that area, with smart converter platforms and so on, communication, automation, condition monitoring, and so on. But also we need to look at the market side. This is also a point that needs to be looked at. At the end, we are providing here different infrastructure in that field that looks from these 3 different angles, mainly to it. Big question is how to plan, operate such a integrated system. And we can here look back on a very long time collaboration. Peter already mentioned in the beginning that the ERIGRID 2 project is an ongoing project similar to the STORIES project, also a research infrastructure project providing transnational access. So we have here, we go back quite long time ago to 2005, where we started a network of excellence in the FP6 program with DELAB. So lots of our members in the integrated grid part are DELAB members. So the DELAB is also part of the consortium. And then we had a couple of different research infrastructure projects that are providing mainly transnational access, but also we started in ERIGRID 2 with virtual access. And this is also what we have here, partly 2 infrastructures in that area that focuses on the virtual infrastructure. But we are offering here in the integrated grid area 10 different infrastructures. 8 of them are physical ones. We have spanned here different laboratories from the north to the south, from the east to the west, more or less in Europe. Different research and technology organizations, universities are offering these infrastructures. And as said, here we have also 2 virtual infrastructures involved, and I will briefly introduce all these 10 different installations, physical infrastructures and the virtual ones. The first one is the infrastructure that comes from my institution, from the AIT. We call it Energy Labs. There are 3 different infrastructures involved. The smartest laboratory is a kind of a power system, smart grid testing environment for inverter-based DR systems, where we can test different, the integration of different converter inverter platforms. under realistic grid conditions. We have a thermal energy storage system lab and also a new facility that's currently in realization, which combines different technologies where we can analyze the grid integration of different generators, but also consumers and storage systems. Another lab that is located in Athens, in Greece, from the National Technical University of Athens. They are focusing mainly on microgrid-based approaches and multi-microgrid approaches. They have here powerful physical equipment, but also simulation equipment. In our area, we are using also quite a lot of real-time simulation system. That means we can emulate the power system, the infrastructure in real world clock time, and connect them with physical equipment like converter systems, but also the ICT equipment. Then we have two additional laboratories, one from Sofia, which focuses mainly on the power system stability. Stability is very important in the electrical grid. So we need to ensure in Europe the 50 hertz more or less closely followed. Smaller or deviations can harm this overall system. So here we have in Sofia, from the Technical University in Sofia here, a laboratory that focuses especially on the system stability. In Romania, in Bucharest, we have the Microtel lab. They are focusing on measurement equipment. It's also very important that you need to identify, or you need to know what's going on in the grid, in the infrastructure itself. So therefore, we have the facility from Bucharest there. Then we are going more to the north, to DTU with the SIS lab and the RISE hybrid power plant approach. Here we have a powerful laboratory that integrates electricity, but also thermal systems together. The grid level on the RISE campus, where they can analyze different control and operation schemes together with hybrid power plants. Then we move a bit to the south, not much, to Oldenburg in Germany, to the office. This is a very specific laboratory also because it doesn't provide really physical hardware equipment. It's a simulation-based laboratory with a powerful ICT equipment. They can analyze large-scale distribution systems, energy infrastructure systems, also in real time, together with corresponding management and operation approaches. Then we have, going up to the north, this is the northest laboratory with SINTEF, with the National Smart Grid Laboratory. Also a powerful laboratory for testing converting inverter systems. They are very specialized on power electronic components and the integration of these components into the power grids. And we're moving far to the east and to the south with the University of Cyprus. Here we have a nice laboratory that focuses on the integration of distributed energy resources, especially photovoltaic systems and their behavior in the power system and the distribution grids. They focus partly on micro and nano grids, as well as energy management approaches. And then, as said, this I would say more specific in RISEnergy, because we have not so many virtual laboratories or virtual approaches, virtual research infrastructures. There are only a few there, and two belong to the cluster of integrated grids. One is the Energy Sim Lab from EIT, and the other one is the VLab from RWH Aachen. Both are kind of simulation as a service approaches where users can connect online to a simulation platform and run different kinds of power system simulation or integrated energy grid simulations. So it's a brief overview about the integrated grids part.
Yeah, thank you, Thomas. I think that fits as a good introduction to the communication part, which comes on top. Michael, please. Funktioniert's? Nicht wirklich.
You are more successful than me.
It seems to have needs a special position.
Okay.
Okay, good afternoon, good evening, everybody. It's a pleasure to be here and meet many of you that in person that we worked with on the proposal. It's very nice for all of us to be here together. As they say, now for something different. I think Peter said in the opening comments, one of the big objectives of this project was to identify what technologies can we bring together and how can we create impact. And ICT is one such technology. ICT to some extent is ubiquitous, it's everywhere, but we have two specific ideas related to ICT that we'd like to talk about in this project, and hopefully we can create some of the impact that Peter spoke about. We're also going to go from the very big stuff. Thomas talked about the grid and the microgrid stuff down to the tiny stuff. So unfortunately, I don't have a huge number of photographs to show you as you saw for many of the other research infrastructures. Instead, I just need you to listen, pay attention, use your imagination, and please come and talk to me and my other colleagues offering ICT research infrastructures. I think we can bring something quite different and potentially something that's quite disruptive to the various technologies that we have here. So the main value proposition that we are putting in front of you here is to look at what we talk about wireless sensor nodes. So the idea here is that we've got these tiny sensors. They can measure things like temperature, light, humidity, pressure. They can do things like acoustic sensing. They can monitor power consumption. And we can retrofit these devices on, in, or near equipment and infrastructure to do various things. One obvious one is to do condition monitoring or to do energy efficiency monitoring. So monitoring the performance of our equipment and infrastructure. How well is it performing? How well is it behaving in relation to maybe a similar piece of equipment that's adjacent to it? How well is it performing in relation to previous energy and performance characteristics of that equipment and so on? So monitoring and seeing how well it's behaving, and is it behaving as expectedly? So that helps us understand the energy efficiency and also can help us with condition monitoring. So this is maybe helping us with things like predictive and preventative maintenance, detecting early when a piece of machinery or infrastructure is misbehaving and potentially is going to go and fail. The other value proposition then is that ICT can be used to enable interoperability between these various systems, particularly the system level, the grid level, energy management systems, such as Thomas talked about. So we have lots of acronyms here: EDM, Energy Demand Management, SES, Smart Energy Systems, DER, Demand Energy Response, EEB, Energy Efficient Building Optimizations, and so on. So a lot of these buzzwords are prevalent in the ICT and indeed in the energy efficiency worlds, but we need to see, can we use some of these concepts by linking various technologies together, and how can we embrace ICT? Now, one thing that's interesting about the value proposition of taking these wireless sensors, normally just run by batteries, and retrofitting them is that we can put them in temporarily or we can put them in permanently. If we put them in temporarily, we're talking about maybe at the development stage, we want to try out, for example, a new type of PV panel. So we want to see how does it compare against previous models that we have. So maybe on a short-term basis, we retrofit these wireless sensors, we capture information and see how well or how badly they're performing, and also how maybe adjacent systems are behaving under different conditions. Of course, further in the life cycle, we can also maybe install these things permanently, that we want to install these sensors, and during the operation of the equipment and infrastructure, we can monitor the performance for efficiency monitoring, predictive maintenance, preventative maintenance of that equipment. And this will help us enhance the performance and reliability of renewable energy systems. But there's a big impediment, and the big impediment is that these wireless sensor nodes need much better battery life than what they experience at the moment. At the moment, a typical wireless sensor node will only last 12 to 18 months. That's fine if we're doing some short-term deployments, but if you're going to be installing these wireless sensors in remote and difficult to access areas, that's not going to cut it, and it's going to be difficult for you to go back and replace these batteries and get these things up and going again. The solution that we're bringing to the table is to bring energy harvesting related technologies, but not energy harvesting as you would know it. This is micro power energy harvesting. So taking tiny amounts of energy, heat, vibrations, thermoelectricity, and converting this to electricity, which will supplement the operation of a battery. It's almost like the Stories project. They talked about hybrid storage. We also need hybrid storage at the micro power level. We want to use a primary battery, but instead of the battery lasting 12 or 18 months, we want that battery to last 10 or 15 years. And the only way we can do that is to harvest using tiny PV panels or thermoelectric devices or vibrational devices, harvest these energies, and for most of the life of these sensors, run them from these ambient energies rather than depleting the battery. So much of the work that we're going to do, hopefully in this project with the feasibility studies, is to talk to people like yourselves and the people who will serve your research infrastructures and understand how can we avail of this energy harvesting technology at the micropower level? How can we retrofit long life battery sensors into our infrastructure so that we can enhance the performance, the reliability, and indeed the interoperability of these systems. Now, a key activity to support this is in work package 3, which I lead, which is called ICT-enabled renewable energy systems. So again, we figured that this was important. I guess this is one of the newest, technologies that we're putting on the table here. Many of you know each other from previous projects, but what we're bringing is quite new. And we figured that a separate task in work package 3 to try and disrupt the technologies that you're developing and bringing in ICT as an enabling technology was required. So that's why we have task 3.1 in there, and I'm leading that work package, and indeed I'll be leading that task. Okay, now there are other research infrastructures that relate to ICT as well. And in fact, I'm sure as we get to know each other, we'll find there are many ICT related research infrastructures already in our ecosystem. It's just that we don't call them as such because it's a secondary element rather than a primary element. But looking through the proposal, 2 stood out to me, and these were TAs 26 and 74. We look at those in a few moments. And what these really are about is bringing in control systems, de-risking control architectures using simulators and hardware interfaces. Research platforms for building an energy district systems, incorporating a multitude of renewable energy technologies so that we can get all these systems to interact and operate on an optimal basis. So let's get into a little bit of detail then. The first research infrastructure that we're offering is from HMU, which is the Hellenic Mediterranean University. It's based in Greece. And they're giving us access to 2 research infrastructures. One is called iMerge, which is from an FET graphene flagship and relates to printed electronics and photonics. You might say, what's the relevance of this? Well, in many cases, printed electronics and photonics enable us to make very, very small, very, very resilient, very, very adaptable, and indeed very, very low power sensors. The second research infrastructure that they have is what they call IEECC, which is the Institute of Environment, Energy and Climate Change. And what they have here really is they have a research infrastructure which relates to energy systems for renewable energy technologies, again, encompassing a wide variety of technologies such as PV, microgrid storage, vehicle to grid, and so on. And they're enabled to do environmental assessments associated with this. So the support offered here it can be either to use these as standalone or maybe to integrate these together, combining the capabilities of the 2 research infrastructures. And indeed, already from talking to some of you during the coffee break here, I think one of the early things that we will discover here is that we may end up doing 2 research. We might end up doing 2 transnational access projects, one at a laboratory basis to tease out the value proposition, for example, in our laboratories in UCC, and then follow on and put it into one of the other research infrastructures, which reflects more of a real-life field application rather than a laboratory environment. So I look forward to discussing this with all of the other research infrastructure owners to see how can we initially tease out the value proposition and then try it in a real life field case. Now, the HMU already have some infrastructure available, as has been indicated with IEECC. They already have some high efficiency PV panel systems available, and they're in a very good starting position now for us maybe to retrofit some sensors and just see how we can further guide and enhance the development of these types of PV panels. This is just some detail regarding the two services offered. As I said, iMerge relates to printed electronics. IECC is an ecosystem of microgrid components where we can do a lot of ICT experimentation, testing the interoperability and controllability of these systems. Okay, on to UCC. This is my home turf. I'm resident at Tyndall National Institute, which is a research center similar to kind of Fraunhofer, but we are our parent organization is University College Cork. Jimmy Murphy, by the way, who spoke earlier on, leading the ocean energy activities, is also from UCC. So what we have available, we are Ireland's largest ICT research centre, 600 people. And what we have really is we can offer the technology to enable us to design and to retrofit and operate the so-called wireless sensor nodes, putting them on in or near equipment and infrastructure. So we have everything from materials to devices to processes, much of it being semiconductor based or MEMS based. MEMS is microelectronic parts, and also doing more and more integration, taking various technologies and integrating together into these miniaturized devices. So what we can do here is that we can leverage our experience in one of the TAs that was mentioned in the opening slides, the Enables project, where we did power IoT research experiments, but applied them to the renewable energy sector. We can assign TAs to HMU or indeed to ourselves to look at the value proposition that we talked about, and we can share best practices. We came up with some very good ideas in the Enables project about how we characterize and make these various technology components available for everybody to use. Again, these are the services that we offer. We can offer ICT enabling access services based around the value proposition. At device level, we can do characterization of components, so we can understand can components that people have in mind be used for renewable energy systems, such as we have in mind with this project. Also, how can we test advanced materials and see how can we do these, and then how do we successfully deploy these types of technologies here. Not too sure if I've got a pointer here. I do, yeah. So, for example, the main message here is that this hybrid energy storage device, it's not easy. Taking ambient energies and integrating them, merging them with an existing primary battery is quite difficult, but we have the technology and the expertise to do this. This is just an example, one of the few photographs that I have. This is a credit card sized. So this is a wireless sensor that runs indefinitely, just measures temperature, light, and humidity for a building energy management application. It uses off-the-shelf solar panel, uses Tyndall power management circuitry. But this device does not need a battery. It runs indefinitely. And this is just showing the concept. We have sensors and detectors. We need to put in processors. We need to put in microcontrollers and transceivers to capture the information and feed that to the various systems. Okay, one last point. I mentioned Jimmy Murphy already. So one thing that we would like to do early in the project is maybe take some of our technology and try it in some of Jimmy's research infrastructure to see, can we really add the value add that we assert in this project and do some early experiments there. And one thing I do know from doing the Enables project is there's nothing like examples. We can talk about conceptually about all the ideas that we have, but it's only when we have some real life TAs done and we've put these on the web and we've advertised these in social media that we'll see what the value proposition is. So Jimmy and I will be working to try and get some of these feasibility studies done early so people can understand what we're talking about. Okay, last slide. There are some secondary TAs. One is from RWTH. So you can see the wording there for yourself. The RWTH RT Lab supports the fast prototyping of control systems and helps the risk control architectures based on off-the-shelf and in-house simulation systems. and looks at the potential merging of advanced research between power systems and ICT. So nice early example of how we can merge. Sorry, go ahead. Yeah, how we can merge. We can bring the ICT and the power electronics domains together. The last one I mentioned is FZJ from Zurich. The Living Lab there as well. I can see there that they again have a multitude of equipment and infrastructure available to us. So looking at the value proposition of embedding ICT research for optimizing the operation of these systems based on some open source ICT platform and for. Now, that's just two that I found. I bet you there's probably 20 or 30 more have some ICT element. Our mission here is to try and bring the ICT, power electronics and renewable energy systems worlds together and see how we leverage from each other and deliver the impact that Peter talked about at the start of this project. Okay, that is it. Thank you.
Thanks, Mike. Very nice homework you did, also identifying potential collaborating infrastructures. Great.
Some early guinea pigs.
Thank you. I think we move on to the next presentation, which is a short notice change. In order to stimulate the discussion, we just decided that it may be better to postpone the cross-cutting and introduce the international REs as the next step by Olga. So please.
Yes, thank you. The real reason is why I'm here and not Holga is because Holga is still not ready. He works on it still. Yeah, I can say I saw it. So those infrastructures you got maybe presented, already heard something about this, but we thought that it would be nice, very nice to show them again, or to show them the first time, as they are not from Europe. Yeah, so we have one infrastructure from Canada, we have one from Japan, we have from USA, and we have from United Kingdom. I think there are 4 of them. Yeah, but when I was checking where they really come from, they're all from Scotland. So it's, yeah, ocean, wind. I think it's clear why it is like this. So I will not go into detail telling what you can do there. I just wanted to show you what we have. So we have materials acceleration platform from Canada. And this infrastructure we know already very well from stories. And yeah, so it's very interesting thing. What it's nice also to know, I put the QR codes everywhere there. So if someone is interested online or here, you can just make a photo of it, and then you will find the web page of this infrastructure. What they do here, as you can see, they work mostly on materials for energy storage, but not only. And that's why we classify it as a cross-cutting infrastructure. Okay, we go to the next one. It's in States, and it's a biomass infrastructure dealing with gasification and pyrolysis of upgrading of biomass-derived syngas and bio-oil. Again, the same situation. I looked for some information about this, this place, and what I found is a very nice movie. And you can just, for people who are interested, you can just go to the movie, have a look what can be done in this facility. The next infrastructure was already presented by Thomas. It belongs to the smart grids, and it's from Japan. I've heard about this infrastructure before. Thomas asked us to take it also to the project. So many of you maybe are already aware about this. Again, the same short movie is there, and I think they can. I don't need to tell too much about this. You can find everything online. Now we go to the UK infrastructures. We have 4 of them. This one is from Glasgow, and it's from Geology Observatory. What they do mostly they work on geothermal energy, and also on the thermal storage. This one is also included in storage project. So Edinburgh fast blade was also mentioned already, I think once or two times. And they work on the tidal turbine blades mostly. We have it here as wind, but also ocean. It was hard to say where to put them. Now we heard from Jimmy, it maybe it would be nicer to have it only defined as ocean, but let's leave it like this here. Next infrastructure also in the north of UK, dealing again with ocean and wind. You can find all the information here, what they are working on. And as I noticed, all infrastructures are somehow combined and they work together. The next one is EMEC, also already mentioned and described very well, I think. So that's the last, let's say, international infrastructure that we have in our portfolio, and also working on ocean energy. So the presentation will be public. You can have a look into the QR codes and just check what is possible there. That was a very short presentation. Now will come the longest one. And Holger, it's your turn, but let's go back.
Yeah, thanks, Holger.
Yeah.
Also interesting different approaches we see here to present the infrastructures and to advertise the information. So I think this bunch of presentation is a nice source of inspiration already. It's very good. And now we move on to a challenging field, the cross-cutting infrastructures. We could talk for hours about that as I cover various aspects. And Holger has the task to give us a glance and introduction into that.
Oh, okay, I managed to handle this. Okay. If somebody doesn't know me, my name is Holger Isen. I'm working for the Helmut Association and for the KIT, and I contributed a bit to this proposal. And Miriam gave me the challenge to discuss the cross-cutting research infrastructures. But I realized that most of the cross-cutting infrastructures were already covered by you, by Courage, by Bernd, by whatever, by Jimmy. Okay, and so you see, so I started my presentation with from zero, and I had the list of the infrastructures given by the coordination team. And there were no pictures, nothing, because then I looked on the internet, and the presentations I discussed, I wanted to discuss with you, are those with pictures on the internet. Okay. Actually, I didn't want to start here with the Energy Lab. I wanted this to start with a general discussion. This is about the cross-cutting infrastructures. In our review report, the reviewers claimed that that was basically the only minus we got. They claimed that we did not structure the cross-cutting energy research community. So basically what they wanted to have is that we say, okay, between grid and storage, for example, there are special researchers, and we should basically look for the users, what is available, and then we make some offers. Okay, my answer to this is we did even more, because we introduced this proactive innovation management, and we are open to everybody who comes to us basically with an application, cross-cutting or not, and then the experts move these people to research infrastructures inside of RISEnergy or even outside. Because, I mean, you run Thomas, for example, Thomas Strasser, I say, is your project still ongoing or is it finished? Is your project still ongoing or is it finished? Yeah, okay, Luca. So if somebody is coming, then we can say, okay, there are much more research infrastructures on grids, and there's a much better fitted one. Please go there. So, I mean, we can focus on a much larger user community, basically. This is the idea of the proactive innovation management here. And if we don't find something, then we can at least set up a list in the future of research infrastructures which are missing. And this is also something the policymakers want to hear from us. Okay. Fine. For the cross-cutting activities, what is missing? I mean, hydrogen was discussed, many other issues. What is missing is the energy systems a little bit. And here's an example, the KIT Energy Lab, where basically you have 3 special tasks which can be done. One is the energy system. I mean, for example, you have a power grid, and then you have special applications. For example, you have a hydrogen storage device, and the question is, how much time does it take to turn on basically the hydrogen device to bring power into the grid? What is the reflection of the stability and so on? And this is not only with hydrogen. I mean, yes, this is coupled with batteries and so on and so on. And there's an addition, Power to X lab, where basically you also try to store hydrogen and feed it back into the network. And you have a carbon cycle laboratory. Okay. Okay. The next one I choose was already presented. I think it's on Sardinia, X to liquids, and from Bernd, I think. And it is basically you have different resources, CO2 from the air, but also plastic and hydrogen, and you try to make fuels out of it. And it maybe does not belong to this presentation here, but I think plastics is an extremely important thing where this whole community could contribute in the future, either with materials research or with something else, to push for new solutions. I mean, plastics is everywhere in our environment. It's, I mean, kind of poisoning us. So people, researchers in the past said it's inert, it doesn't harm us, but it seems to be not true. For example, this PFAS initiative. And I think if this community makes some documents, papers together with the industry, white papers, then I mean, this could help to establish new infrastructures, for example. We have the knowledge from all sides, from ICT, yeah, from materials, from AI databases. And this might help. This is why I have this selected also. Okay, and then we have a special facility at the Heimatzentrum in Berlin, which is a synchrotron, and they make materials research on catalytic materials. Max Planck is also involved here, but they're not participant in the project, I think. Okay, and then we have the IREC Energy Smart Lab, I think is in Barcelona or near Barcelona, and is also in energy, is a grid network, and it has some power emulators and has also some kind of similar challenges than the KIT Energy Lab. This is another point here. Many of our facilities are very similar. And so in principle, what I would like to have is what is very special with your facility? What kind of research can only be done on your facility, and it cannot be done in another RISEnergy research infrastructure. And if you set up the websites, I mean, you should somehow inform the users in this. What is the uniqueness of your facility? Okay, we had this, Jimmy Murphy discussed this. Test center and from CNR, right? You're right. Okay, I don't discuss this again. This was just to show you, okay, we also have large facilities in size. Okay. And then we have a typical materials, research infrastructure, coding laboratory, for, I mean, nearly industrial scale design, 30 times 30 centimeters, includes glass cleaning, then what is PECD? Is a plasma enhanced chemical vapor design, something like this. Magnetrons, sputtering, and lamination units. Okay, well, I made here a long list. I mean, this is basically from the proposal. And then in red, there are my comments where I would put this to. And you see there's a lot of energy systems. And here only a few materials, research devices. On the second page is many more materials. And so we have some clear materials facilities here. Many of those were shown, really. Therefore, it's a waste of time if I go through it again. But okay, so now I talked a little bit, and finally I would start to bring you into the discussions. And the first thing is, I mean, we have, also, as a summary, we have 7 energy systems, research infrastructures, about 6 clear material devices, and a lot of mixtures, PV, CSP, ocean energy, and wind energy, and so on. But for me, when I went through the document or also on the websites of the different research infrastructures, well, it's a little bit confusing. I mean, in the moment, and we need a proper structure on the internet, is my opinion, to order these research infrastructures. I mean, certainly we need keywords, and this is clear. But maybe also a structure like hitting a button and say, okay, I would like to have research infrastructures combining PV, CSP, materials, whatever, and yeah, we should discuss this, how to do it, and who has good examples. I mean, when we drafted the proposals, I remember that I had a problem, and then some of you came and said, okay, we have a perfect solution. This worked very well in drafting the proposal. So we rely on you, yeah. I mean, or the coordination team relies on you. And then the next, I mean, we have basically 1 year time to solve this issue. This is with the access to the research infrastructures. We will have, I mean, we have limited funding, and we will have, how should I say, I mean, from certain areas, the requests of the users will be much stronger than in other areas. And now the project is started, and we also should think about how to solve it. I make you a proposal, the first one. I mean, that we try to share it equally, that is clear. I mean, I don't need to discuss this, but whatever this means. The other thing is, I think we should prefer clear cross-cutting access to the research infrastructures. But then the question is, what is a cross-cutting access? This needs to be discussed. Please, Peter, it's your show now.
Okay, thank you, Holger. So now you see a few questions already here on. But now we have, so to say, presented for more than 2 hours the catalog of infrastructures to you. For me, actually, it was also interesting to see the keywords, the similar keywords popping up in the different areas like coding, materials. Also that infrastructures used in one area could be transferred to another area, which sounds like a very small step, but that also brings the researchers together from one area talking to the colleagues from another one. And that is actually also part of the innovation, to bring people and topics together which normally do not meet. However, I think you have now held back with questions, comments. So now it's up to you. So please feel free to tell us what you think about this. Any opinions, ideas? Even so, that's a coordination team. Olga.
Yeah, I know it's hard to start a discussion. So maybe let's start it in this way. We will have to open a call for the proposals for the users. In month 7, it means in September. How? What should be there in this call? Everyone is invited, present proposal, we check what we will do with it. We cannot do this. We can say Ocean maybe will have a special cool topic, or maybe not. I think we will have to discuss it during the next 7 months in a really way matter that everybody's, let's say, at least a little bit happy. So do you have any ideas how to solve the issue? So maybe we can do like solve the problem of, oh, yes, please, Mike.
Yeah, so I kind of mentioned this in my presentation. I think once people see the transnational access examples, very often they get it, and that very often triggers many other transnational access projects. There's various ways we can do that. One is that many of us have existing or previous research infrastructure projects with websites, with use cases and so on. So I think it would be a good idea for us maybe to maybe go through all of those and maybe put together a collective of TAs that were done under existing and previous studies that we think could be relevant for this.
Yeah.
Kai and
then we share the mic here over.
Yeah.
Yeah, I think from a perspective of the first call, we can't open the door. I think we should open the floodgates because in the beginning, it tends to be a trickle. So I think it's actually the opposite. It is what Mike says. We need to make it very tangible and very open, because we first need to be seen before we can start controlling the valve a little with the narrow topics. That's just one perspective. But I think also both Mike and then Holger emphasized this understanding on what are we offering. We should have a good visualization of what it could be, because understanding what this project is about was very difficult for the participants when we were designing it. So we might as well make an effort and coming up with some good visualizations of the keywords and dynamic presentations of it. I think making it open and rather approachable would be the main point, rather than narrow and ambitious, to be honest.
Okay. Then
Howdy. Hey, yeah, just kind of a tag onto that, and actually speaking from an American perspective, right? You know, I'm only here because I you know, just kind of through osmosis, you know, I knew about, say, the Enables project, working with Mike and various things over the years. Therefore, you know, then learned of RISEnergy. Here I am. But I would say that it's more than a visibility thing, right? But to get to the awareness and education stage. So in other words, you know, especially I deal with a lot of people in you know, the similar kind of IoT harvesting space, especially in the industry. But when I ask people about some of these projects and think some of these EU transnational projects, you know, almost no one's heard of any of these things. And like I said, if it weren't for myself working, you know, close to the mic, I wouldn't have either. So, but my advice is not even just to have a list of say, oh, well, here are these things we've done, just so you know. Even then, that's meaningful to a lot of people in this room. To me, it would be just another list of acronyms that you know I don't have a tangible association with. So until I know that, like, oh, but when I first heard, oh, these transnational program access actually mean that you get access to just this incredible amount of infrastructure, whether they're people resources or other, you know, CapEx resources or whatever. And that was eye-opening to me and enabling, pardon the pun. So that'd be really, and I was actually going to put the challenge back to this team is let me know, you know, what can I do as someone who works, you know, heavily, especially in North America, to help with the bidirectional communication, to you know, help people there understand what's available, how accessible it is, and then of course, then naturally after you've bridged that gap, then you can start working on, you know, better ways to enhance those collaborations.
Mhm. So you mean personal ambassadors are the best promoters?
Yeah, to say
Yeah.
what it is over the pond. No one says, what are you guys doing over there? What are these just at a very high level, even if they don't know the organizations, or, you know, we've never heard of Horizon or, you know, or transnational projects, just knowing that there are these multi-collaborative, you know, consortium-like things that have all these resources that are available. It's just even a list of resources or services. If you said, this is all what's available to you, that would be the exciting, attention-grabbing thing. And then you could say, oh, by the way, these are the, you know, specific projects or institutions or you know, specific resources and how you gain access to get involved. But if you don't get their interest in the first place and just start with, here's a bunch of cool programs and things and resources, they don't know what they're looking at. So they're gonna glance over it. But so that's you got to grab the attention with the really interesting stuff at a high level, and then you can, you know, pull them down the rabbit hole.
Yeah, and that's a good point. I mean, we did not go into the structure in detail of the project, but we have actually a really separate point, which is called innovation management, which should actually support this unit entrance point that if people are interested to learn more about the project, to need help to identify the details actually for a problem they would like to solve or how they can make use of the project, there will be a team supporting that. So we also have it does not need a very detailed preparation to approach the project for a transnational access. You can also come with a general question. I have a solar panel and would like to operate it in a certain environment. Can you help me? And then the project will try to figure out some ways and make the connections to the people.
Actually, Peter, you identified something very important there too, right? Which is to have someone who can translate, right? Not just the resources and things, but like you said, someone who says, oh, I can be oblivious to all that, but here's what I want to accomplish. And there's someone who can say, who sits in the middle, who can, you know, understand enough about the application, about the ask, right? What's being requested, and then and someone who also has visibility to all the resources and can help marry those things, or at least filter the, you know, many institutions resources down to, oh, these are the, you know, the two or three key stakeholders or areas that you want to talk to about this to get them engaged. Yeah. Certainly, because it's a lot of different stakeholders. Sometimes you don't even know what's before you.
Yes.
Yeah, can I just add one other comment? I think one thing that we should also seriously consider is, rather than having an open call and hoping people come to us, we should create a list of target people who would be interested in this. I think we could all come up with a list of 20, 30, 40 names and knock on their doors. I know when I did the Enables project, 70% of our inquiries actually came from industry because that was a big part of our agenda to increase the industry academic engagement. And it's only when we identified who are the people that we think would value the service. And it's only when we went to them specifically, whether we cold called them or whether we met them at a conference or an exhibition, or whether we had links through other people that we knew. It's only when we got into one-on-one discussions with them, and by the way, face-to-face, time with them at a conference or a workshop is a great way to trigger TAs. I've been at conferences where I've actually written 2 or 3 TAs that drafted them at a workshop. So I think we should create a list and go after them.
Yeah, that's a job for us all. We have our networks, we have our project portfolios, collaborators. That's a good point. Yeah, Kurosh.
Yeah, so I just wanted to follow up with the infrastructure, the diversity of infrastructures that are here. There's also limitations of the organizations that hold and owns this infrastructure as well. That's why the project is looking into a lot of different ways. We have seen a fast prototyping facilities that could be easier for a, new supercap technology you want to test, all the way to some testing that requires huge amount of the resource to be there. So my suggestion for success in TNA would be we probably can follow the same thing as a challenge in certain areas, focus on those infrastructure where we can focus on challenges in areas that has to be sort of addressed. At the same time, we have infrastructures that needs more study, more sort of visits, understand of the requirements. Takes longer time to use those facilities. So I think we should have ongoing for those as well as some challenges for specific areas. But I understand what you're saying, but the organizational requirements is a barrier to get things quick, because we can't just get people there to use it. There's a lot of other things. There's a pricing has to be right, and we have to do with a lot of things that comes in. So I think a challenge-based TNA proposal for specific areas that we discussed, in addition to ongoing applications for a longer required sort of planning, would be something that I can suggest as an example, if that makes sense.
So you mean that calls for some thematic calls?
Yeah. Yeah, like for
TNAs.
example, for hydrogen as an example, I brought what the industry is dealing with in batteries, in the grid scale. There are some specific requirements that we know that the facilities are here are responding to that needs. And there are some other things that the person who want to use it has to study whether that setup makes sense or what sort of, the requirements has to go through. So it's not happening as fast as we think it can in some of the facilities.
I think, Holger, that was also one of the questions you had, how to make good criteria for selecting the TNAs, right?
Yeah, I mean, somehow it needs to be an equal share between the different areas. But for me, the key point is still we should move cross-cutting forward. And then the question is, if there are a couple of proposals that are cross-cutting, they should have a priority. Because, this is more or less our job. But the question is, we have to define cross-cutting, because we could, for example, say materials is it just a topic, or it is cross-cutting because it's materials is more useful, or ICT is it cross-cutting, or is it belongs it also to an area? Does it fit?
But isn't it like this that the research can be cross-cutting? The research is cross-cutting, not the infrastructure is cross-cutting, but it depends what you do.
What I'm saying is we need to define this.
Okay, there is a task we have to define the cross-cutting a little bit better. Miriam.
Well, I just wanted to comment in order to disseminate the call. We need for sure the help from the research infrastructure providers, because they know the potential users, of course, we need to rely a bit on that because they know the community on how to disseminate the code. But I do agree that we need to look for other cross-cutting research, not only dedicated in the different fields.
Mm-hmm. Yep.
Yeah, maybe following up on that, I would say for the biofuels area, there is the European Biomass Conference end of June this year in France. That's the community that's active in this field is gathering there. It's about 1,500 people annually. I would say that for the other topics, these conferences also exist. I think that's a good way to launch a call for the transnational access. You have the entire community together, academia, research institutes, industry, and they can benefit from this.
Yeah. I think there are other communities who also have conferences. So that would be a very good information if we get it from the coordination team about these timings and which important conferences we should have in mind. Maybe adjusting a little bit the information material to that. Yeah, Kai?
If no one else. So I think the cross-cutting idea is quite essential for thinking how can we market this project in a simple way. I think go back to that to simplify. And so I'm leader of, I don't know, task 4-3 or something on the training. There we also need to make it simple so people can recognize why are we talking about this. So that's why I'm taking the mic here, because there's a lot of dimensions to cross-cutting, and I was always a bit confused about the term. And my first question is actually back to Holger. Yeah, I know it's in the EU call that there should be cross-cutting, but can we abandon it? So I mean, because it's ill-defined. Not only that, it's also confusing in the sense that you can cross-cut in. As a materials researcher, there's many possible applications. So it's cross-cutting because you get an insight and has many possible value creation. I come from a facility called SysLab. We do systems integration, so it's heat, electricity, coupling things together. But completely different, right? I mean, we don't have the same stakeholders, not the kinds of same visitors that would come to our lab. So if we think in target groups, saying cross-cutting is not helping our purpose. I think we need to be aware of that, and maybe when we start the discussion and make it more concrete, go maybe back a bit to what are the stakeholder groups that we're addressing. And if cross-cutting should be prioritized, we need to understand maybe what are those challenges. I think that was the term that Kourosh used to promote from that perspective. So are there also cross-cutting challenges? Okay, then maybe we learn from that from material scientists what are cross-cutting challenges, and from systems integrators, and that's just 2 words. There's probably other cross-cutting things that I'm not thinking of. So I think that's my main point. Like, let's take cross-cutting sort of as an umbrella term, but not as a communication term. Same is probably true for using TNA for describing a lab access, and so on. So thinking outward focus, thinking about what gets people interested will also help us simplify what is our communication and training activity.
May I jump in? Very simple spoken. This term came actually from the proposal preparation phase, where you can replace cross-cutting with multi-purpose research infrastructures. That means these are the research infrastructures which could be used in more than one thematic area. That was the very first criteria for grouping them into that. I'm not sure. I have the feeling that this term cross-cutting creates a life on its own, which is probably not meant from the beginning. However, there are some cross-cutting aspects which we have seen in the information communication technology and in the grid. The grid is actually the cross-cutting technology which connects the various things. So yeah, probably in the course of the project, we have to be a little bit more careful about this, giving it a special meaning, cross-cutting.
Yeah, so I'm an opportunist, so any technology anybody has, we can bring in ICT as a cross-cutting technology. We can solve your problem.
Yeah.
Sorry, Peter. I just wanted to add something that the objective here is not to promote people to use facilities, is to move the challenges that the energy areas have. And I think that has to stay as an objective. I mean, the idea is to solve the problems of those areas by using the facilities, not the facility usage itself. Just want to make sure if that's really the objective of the project itself.
I would say both.
Okay.
The indicators for success of the project is that we have spent the money for transnational access. Very simple said from EU terms. And then the second question would be, what was the meaning behind? So actually, it's both aspects. And here we simply have to rely on the proposals which come in from the justification the people provide why they would like to use these facilities to let us allow a ranking if we have more proposals than we can support, basically. But yes, we have started out with the challenges here in the area in all your presentations, which was actually quite good, and which could actually be a basis for making more challenge-based aspects into the codes. That may not be relevant for all topics, so we do not need to homogenize this for all areas, but it could be done for certain areas. That we say it's very important, we think we give priority in the first call and the second call to these aspects. Yeah, it's definitely something we need to see then in the steering committee or in the project management committee, in one of these bodies. Yeah, Miriam.
I just like to mention that maybe we should go in a more systematic approach, not only looking at the challenges in the different target areas, but looking at the whole energy system, maybe at the applications oriented at the different sectors that we have, transport, residential, industry. What are the problems in the different sectors and applications, and how can we address these problems and these challenges, and not only looking at the individual technologies? That could be also an option.
Yes.
So everything you're describing sounds like you're converging on something really similar to this work you do in the IEEE group, which is essentially focusing on, in the ICT world about basically energy footprints, right? But anyways, without getting into that, kind of the point is, and to your point before, right, is not, even if it's just the semantics of what you're calling cross coupling, whatever, right? It really is, everything is through, my point of the other example is we classify everything through the lens of energy efficiency. So that is the common unifying thing. If it's a project, right? If it's looking at the energy footprint end to end, right? Or the embodied energy or, carbon total footprint, whatever you like to call it. But that is this RISEnergy, that is your unifying factor, right? Is the energy. So whether it's and whether it's source side in terms of generation, load side in terms of demand, system side where they come together, analysis, utility grid, even a business analysis of energy utilization and footprints. Energy is your common currency. And therefore, if you defined a project around that in terms of energy goals, right? Whether they be footprint, savings, physical reduction of systems or whatever, then intrinsically the rest of the story, I think, can kind of help write itself in terms of what are the specific resources, the teams and available, what do you need to throw at that problem that's constrained by energy metrics and terminology, and then therefore the collaboration kind of happens naturally, or at least what needs to be done becomes more intrinsically obvious. And this worked for us in this other group because this is from the 5G and beyond world. But the point is there's all these black boxes of all this stuff everywhere, hardware, system, business, regulatory resources. How do you connect them all in a meaningful way? And that's what we always converge on, energy. Energy is that common currency. So I can, if that concept and stuff is of use or interest to you, I don't want to belabor it here. I can give you more offline of what we're doing, but just to make, to inspire the team to perhaps, you know, consider a different common metric that still unifies all the objectives.
Definitely, these are, so to say, the overall criteria also behind the call we have to address, and we probably request also information on this, on evaluation and assessment then from all these small projects which are going on, so we can kind of condense this out. I would also say, taking it simple, if you go back home tomorrow with an idea that you say, okay, in my projects, I have this and this consortium, and we would benefit from using installation X, Y, Z from another partner you have not met before, then I think a major goal of this kickoff is already achieved. I can say one story. We are talking about chemical energy storage, and we had the discussion hydrogen from the offshore wind farm or electricity to the shore. Other people think of chemical storage in e-fuels. For that, that means you have to put a chemical plant on a platform close to the turbines. And then aspects come into play that suddenly a distillation column has to be operated also under certain angles and tilting and movements, which is completely new in chemical engineering. And I see here some research facilities which could actually help doing this step faster. So that could be a way of bringing another project group into contact with a group here from that consortium. A very simple thing, but would actually save us another application round and a certain sequence of failures in project application before we actually come to that. So accelerating the thing. So if we think about these maybe smaller or longer, we are not a 5-year, we cannot finance 5-year research activities visits for one installation. It will be time limited, it will be constrained, it should be focused. So if you go out here and you get an idea or even a crazy idea, you would like to think further about it, then I think we have managed a lot already, and you gave a lot of good input and suggestions how to advertise, how to communicate things. So from my side, I would thank all the thematic leaders for putting the effort on a short notice together, preparing this catalog of infrastructures. And I think you all should have a hand.
There are some comments and questions on the chat.
Okay. Holger?
Yeah, I thought I have to do it. Okay. I don't know the recent numbers, but in Horizon 2020, it was like this. Yes, all the research infrastructures in Europe are open to all researchers in the world, to everybody, but the overall budget which we spent on the TNA access, at least in Horizon 2020, should not go above 15%.
Okay.
So this was in Horizon 2020. So.
Thomas?
So the rules are the same as in Horizon 2020. It's 20% of the access units. We can only spend 20% of the access units for non-Europeans.
So the answer is?
European user groups include also the associated countries of Europe. And we have, this is always a challenge. We have such an issue in the Irrigate 2 project where we spend too much access days currently for non-Europeans, because this is always a bit the challenge. On the one hand side, we are measured, or one of the main success factors is the number of access units that we provide as whole consortium. And this is always a trade-off. You get the proposals, you never know how many are coming in over the whole project duration. It is a bit of a challenge to balance that.
So it is possible, but resources are limited. So that needs special attention. So we have to think how we handle this if it comes in to a certain problem. I mean, if we always stay below the 20%, then there's legally no critical issue in it. On the other hand, we have the international infrastructures included, so going out is also possible from Europe.
No, I mean, in our call, I mean, the international infrastructures basically belong to our budget. So overall, I think the Commission would not like to see the international partners go to an international facility. This would be difficult. But otherwise, I mean, the budget, as Thomas said, the boundary is maybe 20%.
Michael?
Yeah, just to relate my experience on the Enables project, it was actually 10%, no more than 10% of our transnational access budget could be outside of Europe. Just going back to Holger's comment, we need to read it, but it's interesting to find out what we do with the international research. But I guess what's in their minds is that if it's an international research infrastructure, it's European taxpayers' money is paying for this, so there has to be some sort of European dimension to every single research infrastructure. But it would be good to get clarification on what the ceiling is. For example, on Enables, we actually had to stop inquiries coming in. We had a lot of inquiries coming in from the Far East and the US, and we simply had to say, sorry, we've already exceeded our limit. So yeah, if we can take that as an action just to figure out what the rules would be, I think that would be good. Thank you.
Definitely a good point. Okay. Other questions in the chat or comments here? And I think we will not lose our time we saved. And before we go for the networking lunch, Holger will tell us an example how we could understand this accelerated innovation a little bit better. So, Holger, again, it's yours.
Okay, I mean, the idea somehow is also that we are a community covering most of the energy fields of real interest, and I think materials is a key issue in the upcoming future for Europe. The reasons might be the critical raw materials, that we need to substitute materials, any other issues. I go into this presentation now. I mean, materials are simply significant. I mean, for example, Airbus, our planes for passengers. I mean, in the 40s, the real difference between planes from the 40s and today is we have composites, we have new materials. That's the reason why they are that big, and many other areas. I mean, the advancement in hydrogen production from electrolyzers is also related very much to the catalytic materials, and so on and so on. So materials are important, and we need to do something. And since a couple of years, we try to use AI in addition and modeling and bring everything together, and we can really accelerate the development of new performing materials much faster. Okay, what we need here in this picture, we have modeling tools, put them in an AI operating system. We have in addition automized synthesis and characterization, and we feed the AI system with the results, and then the modeling basically is improved by the AI system with more to the real results, and better performing materials are quicker found. You see here a plot with photo stabilities from PV materials. And you see the yellow line of tests with a high throughput method. And then if you do it with an AI system, you're much faster. You're more than 10 times faster, and the result is even better than the one which you achieve after thousands of tries with a high throughput method. Just as a proof that what these maps, materials acceleration platforms can do on materials. Okay, but this is not the real challenge. We can do this. And it's done in Erlangen. It belongs to the Forschungszentrum Jülich. And here's the laboratory, and Amanda is the most advanced map I'm aware of. Might be others in Canada, but at least in Europe. Okay, then there are other projects which are focusing on a larger challenge. This is to make new devices with new materials. So a battery is a very complex thing. I think nobody understands really what's going on inside of a battery. It's a perfect field for materials acceleration platforms, because you don't need to understand why this materials is better performing. The result is just better. But the challenge is to bring all these materials together in a device. And the big map is about batteries. And it is how to build this battery together with new materials. And the project is not to find new batteries. The project is to find a way forward how to accelerate research for finding new batteries faster. That's the difference. So, and the challenge is to do this 5 to 10 times. And what is needed here is a large community of research centers, but it's also the knowledge of the industry, how to assemble these batteries. And now, Courage, I stole some of your slides. Okay, there is another project on, it's called Decode, and the main focus is on PEM electrolyzers. And here, I mean, there is also a large consortium here. And again, you have research centers focusing on different areas here, on modeling, on characterization, on whatever, prototyping, testing, and the industry. This is important here, is at the end part of the innovation. And the testing and the prototyping. Okay, now let me transfer this a little bit to other areas. I mean, for example, we could do it tandem PV cells, for example. Yeah, we would like to have a new one with perovskites, for example. Perovskites is a new material. This is not. Is Ivan still here? Just. With the perovskites is new material which is not really stable yet. So something needs to be done, and we have the device, and the Erlangen people are now focusing on perovskites, for example, and there is another field basically where we could bring together industries and research organizations to work on this. Okay, so what is important here? Okay, I try to demonstrate this. So in the moment, we have many conventional approaches to improve materials. There's a huge parameter space, yes, and then we have projects working on it, and a lot of the projects go to the garbage trash, and then the other problem is that the projects are just focusing on certain parameters. They try to optimize the economy, or they try to improve the performance. Maybe they use wrong materials which belong to the critical raw materials, whatever, and so on and so on. So we need to do this more in a better way. And what do we have? So we have a lot of areas of interest which could support our activities. And we have a lot of tools and methods which we try to improve, for example, microscopic theories, structural characterization, and so on and so on. It's a lot of information, and we need to bring this together. How? Okay, again, here we can, an AI system can help us, but the AI system, what does it need? It needs a database which is readable by an AI system. So you need a certain ontology, and this is of critical importance. And if we collect this data from a lot of experiments in a structured way in our community, and we are a large community, and in all our infrastructures, we could try to implement certain AI related ontologies, then we can discuss to build new foundries on other topics as well. I mean, Decode is here working on this PEM electrolyzers. And then the advantage at the very end is you go to your computer, to your AI system, and say, okay, I would like to have a certain quality of economics, performance, and you choose, and you can vary. And then finally, at the end, you get an optimized device, if it really works, finally. But it needs research to do this. And in the moment, I'm only aware of these two projects, which is BigMap for batteries, and with a lot of funding. They will have 40 million euros from the EU, and also support from the in-kind support from the participating organizations, a lot of in-kind contributions, and small-scale Decode project, I mean, relative to BigMap. Okay, what else do we have? I mean, if I discuss this here, what is the impact? Not much. So we need to bring this forward to the policymakers. Okay, then we have the mission innovation activities, bring it forward. This is a worldwide activity on highest level. I mean, this is the German Innen Minister, I don't know the English word. What is this? It's a high level. This isn't. It's close to our Chancellor. They are basically signed the documents for mission innovation, put innovation forward to bring energy technologies ahead. And in 2015, there was the first round, Mission Innovation 1, and they said they want to put more than, would increase the funding for energy-related innovation activities, also on plus 50% on top of it. Okay, it didn't happen, but in their statistics, it happened. I don't know. Anyway, okay. So in mission innovation, there are 7 dedicated missions. One is on hydrogen, one is on power grids, for example. Luciano is leading it. And there are additional activities. They are called modules. One is for insight. They make statistics. One is called accelerator. This is basically innovation should be done by companies. So this is about funding supports. And then there's one called collaboration. And there is a different one on aviation fuel, one on heating and cooling, and one on materials for energy. Okay, and this one, materials for energy, has the objective to push maps forward. And there in mission innovation, they're always co-leads. In the moment, we have Canada and Germany. I am the German co-lead. And the Commission will join soon. This is not official yet, but they will come. And me and Mark Kodrash, who knows him, I don't know, but this Canadian co-coordinator, we focused basically on research activities to bring them together in Europe and Canada, and somehow this worked, and we made slowly progress. The Commission now has a focus to make materials research aware on the highest policy level, which is of course of real interest also for me, yeah, because this might be that will receive more funding here, and this is an opportunity to have also new foundries in other areas for PV, for other things, alloys, whatever. And we should not let this chance pass. Okay, this is what we have on European activities in the moment. This is Big Mac project, Decode. The Helmholtz strategy roadmap on materials is completely focused on maps, meaning this maps are also used for non-energy applications, medicals, plastics, any other materials. Complete, really complete. Then we have a German-Canadian Materials Acceleration Center, which supported by the German BMBF and Canada with 6 million euros. We have now RISEnergy. I will also promote this as mission innovation activity, so to make this more visible. And stories as our storage ecosystem is also belonging to it, and we have a cost action which is coordinated by SACO. Okay, then there are more projects, and they are of real interest, and they are also coordinated partially by Helmholtz. I don't want to go through it, but the key point here is these coordination activities are for industry, and they are completely business related. So they talk to Airbus, for example, what do they do to promote new materials, how to use it. Yeah? So this is the focus, and there's also digitally product passports and things like this. So there's also this connection to these activities. So we have a well-established or structured network. Now the Commission comes with new activities. I mean, we will have these advanced materials partnership so that Europe tries to become industrial leader. Okay, my experience from all partnership is this is mainly for industry. I mean, most of the funding goes to industry. That's just, and there's only a little bit bread falling from the table. And this is for us. That's how you say it in German. So the rest is for you, yeah. And I think for materials research, this is a bad ansatz in mathematical terms spoken, because the key activities are in the research departments. And I mean, we should be able to deliver this information to the industry. And if they build their own materials platforms, then it's okay, but this will take some time. Okay, so we need to focus on kind of business models to collect data, for example, maybe other things as well, to move this forward. I mean, for the AI systems, you have seen this, it's a complicated thing. You need even failed experiments, you need all kind of information which you feed into these modern AI systems. How to do so? Okay, this is it's an approach. I discussed this with Courage. I say this simply. So he's the expert, he's a real expert, and the idea is basically that we set up AI-based databases, and we hope that the Commission or the public hands are supporting them for a while, let's say 3, 5, or 10 years, and we collect data and information so that they become useful for the devices. And then at certain, the Commission always, all activities are stopped after a while. This is policy. And this will also happen in this case. And then, I mean, if the database is of interest for industry and for the users, then, I mean, we can take a fee from them. So this is the basic idea. There's another slide how this could look like, but I skipped it. I mean, if you want to have more information, Courage is the expert. I'm only the guy who brings this into the community. Okay, so now the what can we do? Okay, the mission innovation people will meet with the commission and also with the member states. And this is, I mean, this is in April. So if you have any ideas, yeah, basically to feed this, what do we need in the future, then I'm happy to talk to you. So my idea would be that we try to establish some kind of an S3 infrastructure network. I mean, we have a couple of established maps, but we don't need only maps. I mean, in Erlangen or in, also the big map is in Ulm. We have some in Canada. Canada is also associated in the moment. This is not sufficient. We also need the industry participating in a kind of network, and we have these databases. The database could also be funded by an S3 support structure. So we could try to advertise this also as RISEnergy community in other areas, PV, for example, tandem cells, to go ahead. Alloys are key importance for the devices to keep them stable. Okay, and okay, this is my point here, and this would be also a way forward to integrate us into the partnership, because then we could offer to the partnership a way forward and say, okay, I mean, we have this network here of activities. We have a database. The industry can connect. Maybe they can pay even through the partnership. And we make excellent accelerated research on the activities. Yeah, that's it, basically, what I want to say. So if you have good ideas, please come to me how to bring the industry together with our materials research. We have a kind of network, but it's not, I mean, there is no signature between the parties. And this is what we need if you want to establish a database. Thanks.
Thank you, Holger. Actually, these activities, we are expected to contribute to that, and we also have 3 tasks in work package 3 actually, which are somehow connected to these activities. So it's an activity we are actively considering here as well, and it's much more going on the international scheme. Are there questions, burning questions for Holger at the end of a long day? Everything was clear?
Come on with your ideas.
Okay. Then for idea generation, we have actually the networking lunch now. And before we go to this, let me just remind you, tomorrow we start at 9 o'clock, again here. As I was told, the room is closed after this session. They're doing some cleaning, so you have to take your belongings, coat and bags and so on with you out. There's a cloakroom downstairs where you can put this. We will have a networking dinner outside prepared. If you have any dietary requirements, please contact the catering staff and the service. They are happy to help you. I think we have covered all the variants. Yeah, you normally cover here. So if something is not very clear from the labeling or so on, just ask. And with this, I would like to close the session for today and see you again tomorrow. Or have a good discussion later on.